Look up at the night sky, and you'll likely see a single, brilliant point of light, our sun, solitary and steadfast. But what if you lived in a reality where your sky was filled not with one star, but with 10? Picture this: 10 individual suns, each a colossal furnace of incandescent plasma, all dancing around a shared center of gravity in a celestial ballet of unimaginable complexity. This is not science fiction. This is the staggering reality of a decuple star system. We are venturing far beyond the familiar territory of binary stars, which are common enough, into a realm where the very laws of physics are stretched to their absolute limits. In these systems, gravity doesn't just create a simple partnership. It weaves a chaotic, ever-shifting web of cosmic interactions, a place where days and nights, if they could even be defined, would be a constantly changing tapestry of light and shadow. It is one of the most extreme and bewildering environments the universe has to offer, and the discoveries emerging from their study are rewriting our understanding of stellar behavior. These are not peaceful arrangements. They are cosmic arenas of perpetual gravitational tug-of-war, where orbits can be wildly unstable, and the fates of stars are intertwined in a high-stakes dance that can last for eons or end in cataclysmic violence. The sheer existence of such a system challenges our intuition and forces us to ask profound questions about how stars form, how they evolve, and what kind of bizarre phenomena can occur when nature decides to pack so much raw power into one place. The journey to understand decuple star systems is a journey to the very frontier of astrophysics, a place where every new observation can overturn old assumptions. And it is within these dizzying cosmic architectures that astronomers have uncovered some of the most peculiar and astonishing secrets of the galaxy. From stars that steal material from one another in a frantic struggle for survival, to the potential for planetary orbits so chaotic they defy prediction, the findings are as strange as they are enlightening. We are about to embark on an exploration of 30 of the most mind-bending discoveries about these 10 star systems, each one revealing a new layer of the universe's capacity for wonder and mystery. This is a story of cosmic extremes, of beauty and chaos intertwined on a scale that is almost impossible to comprehend, and it promises to change the way you see the night sky forever. Our journey into this realm of stellar extremes begins with a single, perplexing point of light in the constellation of Cassiopeia. For generations of astronomers, the star known as Cassiopeia appeared to be just another variable star, its brightness flickering in a pattern that was maddeningly difficult to decipher. Initial observations revealed not a simple rhythm, but a chaotic symphony of light curves and radial velocity changes, where the star's spectral lines would shift back and forth in a way that defied any conventional explanation. It was as if they were listening to a complex piece of music with 10 different instruments all playing at once, but could only hear the combined noise. For decades, this system was a celestial puzzle box, with researchers slowly and meticulously gathering data, trying to isolate the individual gravitational signatures within the cacophony. The breakthrough came not from a single eureka moment, but from the patient accumulation of evidence over years, then decades of observation. Advanced spectroscopic techniques and long baseline interferometry finally allowed astronomers to separate the signals, to untangle the gravitational dance and make the astonishing confirmation. They were not looking at one star or even a common binary, but at a system of 10 distinct stellar bodies all bound together in an intricate gravitational embrace. The architecture of Cassiopeia is a cosmic hierarchy of staggering proportions. At its heart lies a tight core of massive, brilliant stars, O-type and B-type giants that dominate the system with their ferocious energy output and powerful stellar winds. These central behemoths are themselves locked in close, fast orbits, whirling around one another in a dizzying display. Further out, a second tier of smaller, yet still significant, stars orbit this central core, their paths influenced by the combined gravity of the inner group. And completing this celestial family are a number of lower mass red dwarfs, the faint, smoldering embers of the system, tracing wide, slow paths on the outskirts. The confirmation of AR Cassiopeae as a decuple system was a monumental milestone, fundamentally altering our perception of what is gravitationally possible. It proved that star formation could, under the right conditions, produce not just twins or triplets, but entire litters of stellar siblings that could remain stable, or at least metastable over astronomical timescales. This was no theoretical curiosity. It was a real-world laboratory for testing the limits of orbital mechanics, a place where the simple two-body problem we learn in physics class gives way to the nightmarish complexity of the n-body problem. The very existence of AR Cassiopeae challenged astrophysicists to develop new models and simulations to understand how such a system could form without immediately tearing itself apart, forcing a re-evaluation of the processes within the dense stellar nurseries where stars are born. It stands as a testament to the fact that the universe is often far stranger and more wonderful than our most ambitious imaginings. Once astronomers confirmed the existence of a system with 10 stars, the immediate, burning question was how such an arrangement could possibly hold itself together. The intuitive assumption might be a scene of pure chaos, with stars careening unpredictably in a gravitational mosh pit, destined for a swift and violent disintegration. Yet the reality is far more structured and in its own way even more astonishing. These systems defy collapse not through randomness, but through an intricate architectural principle known as hierarchical stability. Imagine a set of Russian nesting dolls where each doll you open contains another, smaller doll inside. Now translate that into gravity and motion. In a decuple system, you don't have 10 individual stars all pulling on each other equally. Instead, gravity creates a series of partnerships, a cosmic dance of pairs within pairs. At the most fundamental level, you find tight binary stars, two suns locked in a close, intimate orbit, whirling around each other in a matter of days or even hours. These pairs are the fundamental building blocks, the smallest and most stable gravitational units. Now take two of these tight binary pairs. They themselves can be gravitationally bound, orbiting a common center of mass at a much greater distance. This creates a quadruple system, a stable quartet where the individual pairs are so far apart they essentially behave as single, massive objects in a wider dance. This process of stacking continues. Two of these quadruple systems can then orbit each other, creating an octuple arrangement. And finally, to complete the decuple, a pair of solitary stars, or perhaps another tight binary, can be found tracing a vast, slow orbit around this entire central hub. The beauty of this hierarchy is that it simplifies the gravitational nightmare. For a star in the innermost binary, its immediate gravitational environment is dominated by its single partner. The overwhelming pull of the other 8 stars is softened by distance, acting as a gentle, combined tidal force rather than a disruptive, direct yank. This layered structure prevents the system from descending into an unpredictable frenzy, creating pockets of local stability within the grand, complex whole. To visualize this, think of our own solar system, but with every component replaced by a binary star. Instead of a single sun at the center, picture a pair of brilliant stars orbiting one another. Where Earth would be, imagine not a solitary planet, but two worlds locked in a perpetual dance around each other, while the pair itself orbits the central binary suns. Jupiter's orbit would be occupied by another binary pair of gas giants, and so on out to the Kuiper belt. In this analogy, every planet is itself a miniature stellar system, and the entire assembly is a coherent, albeit immensely complex, structure. This nested configuration is nature's elegant solution to packing an enormous amount of mass and gravitational influence into a relatively confined space without triggering immediate collapse. It's a testament to the universal laws of physics that such a delicate, multi-layered balance can be achieved and sustained, sometimes for billions of years. The stability of these cosmic Russian dolls hinges on the relative distances between each level of the hierarchy. The inner binaries must be tight, and the orbits of the outer pairs must be sufficiently wide, creating a clear separation of gravitational influence. When this delicate spacing is maintained, the system can persist, offering a stable, though profoundly complicated, home for any potential planets. This hierarchical principle reveals that the universe has a preferred method for building complex systems, favoring structured organization over random chance, even in its most extreme and crowded stellar neighborhoods. But as we celebrate the discovery of these 10-star families, we must also acknowledge the cautionary tales that remind us just how difficult it is to definitively map such complex systems. The quest to identify a true Decuple system is fraught with ambiguity, and sometimes what appears to be a stellar family of 10 is actually a case of cosmic mistaken identity. This leads us to a fascinating class of objects we might call the failed Decuple systems, where initial observations suggested a full house of 10 stars, but deeper investigation revealed a very different reality. One of the most compelling examples of this involves a system catalogued as HD 98800, a complex arrangement located about 150 light-years away. For a time, data from powerful observatories painted a picture of incredible complexity, with spectroscopic and photometric signals hinting at the gravitational influence of as many as 10 distinct bodies. The idea of a Decuple system so relatively close to us was electrifying, but the truth, once uncovered, proved to be even more intriguing. Further analysis, particularly using high-resolution infrared telescopes, revealed that one of the key components originally counted as a star was in fact something else entirely, a brown dwarf. Brown dwarfs are the enigmatic misfits of the cosmos, often called failed stars. They form like stars from the collapse of a gas cloud, but they simply don't have enough mass to ignite sustained hydrogen fusion in their cores, the defining characteristic of a true star. They occupy a murky middle ground, more massive than the largest planets like Jupiter, but smaller and cooler than the smallest red dwarf stars. The presence of a brown dwarf in a system like HD 98800 fundamentally changes its classification. While the system is still incredibly complex, it is a quadruple system composed of 2 binary pairs. It falls short of the Decuple milestone. The brown dwarf is a gravitational participant, a significant source of mass, but it is not a star. This discovery highlights a fundamental challenge for astronomers. Distinguishing between a dim, low-mass star and a bright, high-mass brown dwarf from a great distance is exceptionally difficult. Both can have similar temperatures and emit light in similar ways, especially in their youth. The key lies in measuring their mass with extreme precision, a task that often requires years of patient observation to track their orbital motion. The HD 98800 system serves as a perfect illustration of the blurred line between different classes of celestial objects. It forces us to ask what truly defines a star. Is it solely about the physics of fusion, or is it about its gravitational role within a system? A brown dwarf, while not a full-fledged star, can be just as massive and gravitationally influential as a small star, capable of clearing its orbital path, possessing a system of moons, and even influencing the orbits of other true stars in a complex dance. This gray area extends even further. In other candidate systems, what was initially interpreted as a faint stellar companion has sometimes been revealed to be a massive, Jupiter-like exoplanet, a world so large it mimics the spectroscopic signature of a small star. These discoveries underscore the immense technical hurdles in our search for the universe's most extreme stellar families. It's a bit like trying to count the number of people in a crowded, dimly lit room from 100 yards away. You might see 10 distinct shapes, but upon getting closer with a better camera, you realize one of them is a life-sized mannequin and another is a very tall person standing on a box. The initial count was made in good faith, but the reality requires a more nuanced understanding. These failed Decuple systems are not failures of science. They are triumphs of our ever-improving technology and analytical methods. They push our instruments to their limits and force us to refine our definitions, reminding us that the universe is not always easily categorized. The journey to confirm a true 10-star system is as much about eliminating these fascinating imposters as it is about finding the real thing. Perhaps the most startling revelation to emerge from the study of these complex stellar families is that planets can and do exist within them. The notion of a world orbiting not one but a shifting ensemble of 10 suns seems to defy all common sense. We are taught that planets form in the quiet, placid disks of gas and dust encircling a single infant star, a gentle process that requires a stable environment. Yet, here we find worlds that have somehow coalesced and endured in what can only be described as a gravitational maelstrom. The discovery of these rogue planets, untethered to any single star, forces a complete rewrite of our theories on planetary birth and survival. In a Decuple system, the traditional circumstellar disk, the tidy, rotating platter of material from which planets are built, is an impossibility. Instead, the entire system can be swaddled in a vast, chaotic circumsystem disk, a dizzying whirlpool of dust and gas that feels the competing gravitational tugs of all 10 stars. Within this turbulent disk, the process of planet formation becomes a frantic, almost violent affair. Clumps of material struggle to coalesce as passing stars stir the pot, creating shockwaves and density fluctuations that can either trigger the rapid assembly of a planet's core or tear a budding world apart before it can fully form. That any planet could emerge from this cosmic riot is a testament to the sheer stubbornness of matter to clump together under gravity's influence. The very existence of these planets suggests that planet formation is a far more robust and opportunistic process than we ever imagined, capable of occurring in the most hostile and unstable of neighborhoods. It implies that the seeds of worlds are sown everywhere the conditions allow, even in the midst of a stellar hurricane. The planets that do manage to form in such an environment are likely to be extreme worlds, perhaps massive gas giants built from the abundant material in the outer reaches of the disk, or hardy, rocky planets that somehow survived a bombardment of gravitational perturbations during their infancy. Their very presence is a profound challenge, indicating that our models of planetary genesis, while successful for calm systems like our own, are far from complete. They reveal a universe where planets are not a rare privilege of solitary stars, but a common, almost inevitable, outcome even in the most crowded and chaotic of stellar apartments. If the birth of these worlds is a mystery, then their potential orbits are a full-blown enigma. A planet in a 10-star system cannot simply trace a neat, elliptical path around a central point. Its trajectory must be a convoluted, weaving dance, a complex path dictated by the ever-changing balance of gravitational forces. At times, the planet might be firmly within the grip of one tight binary pair, effectively orbiting their shared center of mass. As it travels along its path, the distant pull of another stellar group will gradually begin to influence it, tugging it into a wider dance around a quadruple core. For a brief period, it might even find itself orbiting a single, brilliant star within that group, before being slingshot back out into a grand orbit encompassing the entire system. This creates an orbital map of staggering complexity, a path that is not a simple, repeating ellipse but a constantly evolving figure 8 or a rosette pattern that never exactly retraces its steps. These are not stable, predictable orbits like those in our solar system. They are stable, chaotic orbits. This is a fascinating paradox where the planet is not immediately ejected, yet its long-term future is fundamentally unpredictable. Tiny, imperceptible changes in its starting position or velocity can compound over thousands of years, leading to wildly different fates. One path might keep it safely weaving between the stars for billions of years, while another, nearly identical path, might send it careening into the heart of a stellar group or flinging it out of the system entirely to become a lonely interstellar rogue. Imagine trying to navigate a boat through a harbor where 10 massive, moving whirlpools are constantly shifting position, their currents pulling you in different directions. Your course would be a continuous series of corrections and adjustments, a precarious balance where a single misstep could lead to disaster. This is the daily reality for a planet in a Decuple system, a perpetual gravitational tightrope walk where stability is a fragile and temporary state. The existence of such orbits demonstrates the incredible richness of gravitational dynamics, showing that what we consider normal in our quiet solar system is just one simple solution in a vast cosmic library of possibilities. The ultimate consequence of this orbital pandemonium is the complete demolition of our conventional idea of a habitable zone. In our solar system, the concept is beautifully simple. A slender, shell-like region around our sun where the temperature is just right for liquid water to potentially exist on a planet's surface. But what does distance from the star even mean when you have 10 of them? The habitable zone in a Decuple system is not a placid, static ring. It is a shimmering, pulsating, and fragmented volume of space that morphs and twists with the intricate dance of its stellar host. A planet on its chaotic journey would experience wild and dramatic swings in stellar insolation. For a period, it might be nestled close to a pair of brilliant O-type stars, bathing in intense, searing ultraviolet radiation that would sterilize its surface and strip away any atmosphere. Later in its long orbit, it could drift into the cooler, dimmer domain of the system's outer red dwarfs, where sunlight is a faint crimson glow and the world would freeze into a global ice ball. The only potential for habitability would exist during the fleeting, transitional phases where the planet passes through a Goldilocks sweet spot, a temporary alignment of distances and stellar intensities that briefly offers moderate temperatures. Life as we know it would face an unimaginable challenge. It would need to be incredibly resilient, perhaps existing in deep subsurface oceans shielded from the violent shifts in climate, capable of entering long periods of suspended animation during deep freezes or hunkering down during scorching infernos. The day-night cycle itself would be a spectacle of pure chaos. There would be times of multiple suns in the sky, casting a complex web of shadows, followed by periods of perpetual daylight from one direction, or perhaps a true night where only the faintest stellar embers are visible. The very rhythm of life would be dictated by this unpredictable celestial clock. This forces us to expand our definition of habitability beyond a simple, stable orbital distance. It pushes us to consider life that is not just tolerant of change, but thrives on it, evolving in an environment of extreme and regular disruption. The discovery of planets in these systems, therefore, doesn't just tell us about where worlds can form. It fundamentally reshapes our search for life itself, suggesting that if it can take hold in the most tumultuous of cradles, then it might be far more widespread and tenacious than we ever dared to dream. Even in the carefully choreographed hierarchy of a Decuple system, the dance of 10 massive bodies is never perfectly safe. With so many participants in a confined gravitational space, close encounters are not just a possibility, they are an inevitability. The complex, interweaving orbits mean that stars, particularly those in the inner binary cores, can swing perilously close to one another. And when they do, they unleash a force of nature so powerful it can literally tear a star apart, not with a cataclysmic impact but with a relentless gravitational pull. This is the realm of extreme tidal forces, a phenomenon that transforms these stellar neighborhoods into cosmic forges of bizarre and hybrid objects. Tidal force is simply a difference in gravity. You experience a mild version of it every day. The moon's gravity pulls more strongly on the side of Earth facing it, slightly stretching our planet and creating the ocean tides. Now amplify that concept to an almost unimaginable degree. Picture two stars, each hundreds of thousands of times more massive than our entire planet, passing within a few stellar radii of each other. The side of one star facing its passing partner feels a gravitational pull exponentially stronger than the side facing away. This difference doesn't just create a gentle bulge, it generates a force so violent it can overcome the star's own gravity, the very force that holds it together. The star begins to deform, no longer a perfect sphere but a teardrop shape stretched towards its gravitational assailant. As the stars reach their closest approach, this stretching escalates into a catastrophic distortion. Vast streams of superheated plasma, the very stuff of the star's outer layers, are pulled free. These immense rivers of gas, glowing at temperatures of tens of thousands of degrees, flow from one star to the other, or are flung out into the system entirely, creating a temporary bridge of incandescent matter between the two celestial bodies. This process has a famously vivid name, one borrowed from the physics of black holes: spaghettification. It's the precise term for how extreme gravity stretches an object into a long, thin strand. While we typically associate this with the unimaginable forces at the event horizon of a black hole, the same fundamental physics operates on a grand stellar scale within these crowded systems. A star doesn't need to be consumed by a singularity to be turned into cosmic poster. A close brush with a stellar sibling can achieve a similar, if less final, effect. The result is not merely a spectacular light show. This violent transfer of material has profound and lasting consequences for the stars involved, effectively rewriting their life stories. Consider a scenario where an older, puffed-up red giant swings too close to a younger, hotter, and more compact main sequence star. The red giant, with its tenuous grip on its outer layers, is highly vulnerable. The compact star acts like a gravitational vacuum cleaner, siphoning off enormous amounts of hydrogen and helium from its larger companion. This stolen fuel rains down onto the surface of the younger star, reigniting nuclear fusion processes with a new and unnatural intensity. The receiving star can become overluminous, burning hotter and brighter than it should for its age and mass, essentially rejuvenated by a cosmic meal it never earned. It becomes a stellar Frankenstein, a hybrid object with the composition and behavior of a star that has lived two different lives simultaneously. The donor star, meanwhile, is left scarred and diminished. Stripped of its outer envelope, it may reveal its hotter, denser core prematurely, abruptly ending its life as a red giant and transforming into a helium-burning star or even a white dwarf far sooner than its natural timeline would allow. This mass transfer can also create some of the most peculiar and energetic objects in the galaxy. If the receiving star is a white dwarf, the influx of fresh hydrogen from its companion can trigger runaway fusion on its surface, leading to a cataclysmic nova explosion that can briefly outshine an entire star system. In even more extreme cases, if enough mass is dumped onto the white dwarf, it can push it over the Chandrasekhar limit, causing it to detonate completely as a Type Ia supernova, a titanic event that can sterilize the entire Decuple system. These stellar interactions are not gentle mergers. They are violent, transformative events that can alter the fundamental properties, compositions, and ultimate fates of the stars. They create a dynamic environment where stars are not isolated islands, but deeply interconnected, their evolution dictated as much by their gravitational relationships as by the nuclear fires burning in their cores. The presence of these mass transfer streams and stellar hybrids serves as direct, observable evidence of the fierce gravitational tides that constantly reshape the lives of stars within these most extreme of families. Yet even the dramatic transformations caused by tidal forces are not the most immediate threat to any potential worlds in a Decuple system. That distinction belongs to an even more violent and instantaneous phenomenon, the superflare. In our own solar system, we are familiar with solar flares, powerful bursts of radiation that erupt from the sun's surface. These events can disrupt satellites and create beautiful auroras, but they are mere firecrackers compared to the cosmic detonations witnessed in systems with multiple stars. Within the crowded confines of a Decuple family, the stage is perfectly set for magnetic mayhem on an unimaginable scale. Many stars, particularly the younger, faster-spinning ones, generate powerful magnetic fields. Normally, these fields are complex but largely confined to the star itself. However, when several such stars orbit closely, their magnetic fields don't just coexist, they interact, tangling and braiding together in a web of immense energy. Picture the most powerful thunderstorm you can imagine, then multiply its energy by a factor of millions and confine that fury into magnetic ropes connecting 10 different stars. This creates a system-wide circuit of stored power, a capacitor charging relentlessly until it can hold no more. The result is a superflare, a catastrophic release of energy that makes the largest eruption from our sun seem utterly insignificant. While a major solar flare might release energy equivalent to 1 billion megatons of TNT, a single superflare from an active star in a Decuple system can unleash the power of 100 million suns in one ferocious burst. It is a flash of radiation across the entire electromagnetic spectrum, from radio waves to gamma rays that can, for a few terrifying minutes, outshine the star itself. The consequences of such an eruption for any nearby planets are nothing short of apocalyptic. The first wave to arrive is the extreme ultraviolet and X-ray radiation, a pulse of energy so intense it would act like a blowtorch applied to a planet's atmosphere. For a world orbiting anywhere in the system, this initial blast would rapidly ionize the upper layers of its air, stripping electrons from atoms and molecules and beginning the process of atmospheric erosion. But the true devastation follows close behind in the form of a coronal mass ejection, a colossal bubble of magnetized plasma, traveling at a significant fraction of the speed of light. Because the stars are so close together, this relativistic projectile would not take days to arrive as a coronal mass ejection from our sun takes to reach Earth. In a Decuple system, it could cross the space between stars in a matter of hours or even minutes. When this directed energy weapon of cosmic proportions strikes a planet, the effect is total sterilization. The planet's own magnetic field, if it has one, would be utterly overwhelmed, compressed and shredded by the onslaught. The incoming plasma would then directly bombard the surface, scouring it clean of any complex molecules and boiling away oceans in an instant. The delicate chemistry that could support life would be seared away, leaving behind a barren, molten rock. A single such event, originating from just one of the 10 stars, has the potential to reset the clock for habitability on every single planet within the entire system simultaneously. This changes the entire equation for life in these extreme environments. While a planet might occasionally find itself in a transient, temperate orbit within a fluctuating habitable zone, its long-term survival would depend on sheer luck, hoping that during its brief windows of climatic stability, none of its stellar neighbors decide to unleash their magnetic fury. It creates a cosmic version of Russian roulette, where the gun is pointed at every planet in the system, and the trigger is pulled whenever the tangled magnetic fields of these stars suddenly snap and reconnect. This discovery forces astronomers to add a new, critical dimension to the concept of the habitable zone, not just a region of suitable temperature, but also a zone of magnetic safety. A planet must not only be in the right place for liquid water, but it must also be far enough from the most magnetically active stars to avoid being periodically scoured by these lethal blasts. The existence of superflares in Decuple systems reveals that stellar violence is not merely a local phenomenon. It is a system-wide hazard, a shared existential threat that connects the fates of every world in a way that is both terrifying and awe-inspiring. Now, imagine being an astronomer carefully tracking the intricate dance of 9 brilliant stars, meticulously plotting their orbits over years, only to realize your calculations are consistently, maddeningly wrong. The paths you observe, the subtle wobbles and unexpected accelerations simply don't add up. No matter how you model the gravitational pull of the 9 visible suns, there's a ghost in the machine, an invisible hand tugging at the entire assembly. This is the enigma of the dark gravitational partner, a discovery that transforms a complex stellar system into a cosmic murder mystery. The evidence isn't a flash of light or a burst of radiation. It's a profound silence in the data, a void that speaks volumes. The orbits of the 9 stars, particularly those on the outskirts of the hierarchy, exhibit a telltale drift. They behave as if they are orbiting a massive, unseen object at the system's edge, an object with a gravitational signature so potent it must contain the mass of several suns, yet it emits no light, no heat, no radio waves. It is a celestial phantom, revealed only by its influence on the luminous actors in the play. The immediate detective work for astronomers involves a rigorous process of elimination, systematically ruling out every other possible explanation for this gravitational anomaly. The first and most hopeful suspect would be a very dim star, like a cool, faint red dwarf or a brown dwarf. But even the dimmest true star would still emit a detectable infrared glow, a warmth that our most powerful space-based telescopes should be able to pick up. When repeated deep sky surveys scan that precise location in multiple wavelengths and find nothing but empty blackness, the dim star hypothesis crumbles. The next possibility is a rogue planet, a Jupiter-like world of immense size. But here, the math betrays this idea as well. The amount of gravitational influence required to perturb the orbits of multiple stars indicates an object far too massive to be a planet. Even a so-called super-Jupiter, the largest class of planet we know, would be gravitationally insignificant in this titanic tug of war. It would be like a pebble trying to alter the course of a freight train. The invisible object, based on its gravitational pull, must possess a stellar mass several times that of our own Sun. With a dim star and a giant planet both conclusively ruled out, the list of possible culprits grows very short and very dark. This leaves one profoundly thrilling possibility, a stellar mass black hole. This would be the remains of a massive star that lived a short, violent life and ended it in a supernova explosion, its core collapsing into an object so dense that its gravity prevents even light from escaping. The fact that it now resides within this Decuple system suggests a dramatic past. This black hole is likely the ghost of a 10th sibling, a star that was once a vibrant member of the family before it catastrophically died. Its continued presence means the supernova explosion, while violent, was not perfectly symmetrical. A so-called kick from the detonation was not strong enough to eject the black hole from the system's gravitational grip. It now silently stalks its family, a dark sentinel whose only interaction with the universe is through its immense gravitational field. Its location, often inferred to be in a wide, slow orbit around the system's core, makes it the ultimate hidden predator. It doesn't actively feed or create a bright accretion disk because there is no readily available source of gas to pull in from its stellar siblings, which are all stable and secure in their own tight orbits. It is a black hole in hibernation, its terrifying power dormant but ever present. The implications of a black hole lurking within a Decuple system are staggering. It introduces a permanent element of long-term, existential risk that far surpasses even the threat of superflares. The black hole's gravity acts as a persistent source of orbital perturbation, slowly injecting chaos into the delicate hierarchical balance over millions of years. It could gradually destabilize the wider orbits, potentially flinging one of the outer stars or binaries out into interstellar space, or, in a far more dramatic scenario, steering it onto a collision course with another member of the system. Furthermore, this discovery provides a rare and precious opportunity for astronomers. Confirmed stellar mass black holes are notoriously difficult to find because they are, by their very nature, invisible. We usually only detect them when they are in a binary system with a visible star, actively pulling material from it and creating an X-ray emitting accretion disk. A quiescent, isolated black hole like this one is the proverbial needle in a haystack. Its presence in the Decuple system offers a unique laboratory to study the gravitational effects of a black hole in a relatively clean environment, allowing scientists to measure its mass with precision and observe how its gravity sculpts the dynamics of a complex family of stars over time. It is a silent, dark anchor around which the fate of an entire stellar dynasty may ultimately revolve, a reminder that the most powerful forces in the cosmos are often the ones we cannot see. After confronting the terrifying possibility of hidden black holes and sterilizing superflares, you might assume that every Decuple system is a ticking time bomb, destined for a short and violent life. Yet, one of the most profound discoveries in this field completely shatters that expectation. Astronomers have uncovered systems that, against all odds, have achieved a state of perfect gravitational harmony, persisting in their intricate dance not for mere millions but for billions of years. This longevity defies the intuitive chaos of the n-body problem and points to a deeply ingrained order within the apparent pandemonium. The key to this remarkable stability lies in a phenomenon known as orbital resonance, a delicate and precise gravitational synchronization that transforms potential chaos into a long-lasting cosmic ballet. Consider the specific case of a hypothetical yet scientifically plausible Decuple system we'll call Kepler's orrery, modeled in exquisite detail by supercomputer simulations. In this system, the 10 stars are not just randomly arranged, their orbital periods exist in neat integer ratios with one another. For instance, for every single completed orbit of the outermost binary pair, the central quadruple system completes exactly 2 full rotations, and the innermost tight binary pirouettes precisely 5 times. These are not mere coincidences, they are the fundamental gears of a celestial clockwork. This resonant locking means that the gravitational tugs between the stars become predictable and repetitive. Instead of chaotic, cumulative pulls that would gradually destabilize orbits, the stars exert their strongest influences on each other at the same points in their cycles, creating a rhythmic pattern of gentle, correcting nudges. It's the difference between trying to push a child on a swing at random, ineffective intervals and pushing them at the exact peak of their arc every single time, building a stable, predictable rhythm. In Kepler's orrery, these resonant pushes maintain the balance, ensuring that no single star ever receives a net gravitational kick that would send it spiraling out of control. This gravitational harmony creates a series of protective barriers within the system. The resonances effectively carve out safe zones, similar to the Lagrange points in our own solar system, where the competing gravitational forces cancel each other out. Within these zones, the orbits of the stars become protected or shepherded from disruptive close encounters. The entire configuration operates like a meticulously engineered piece of music, where each stellar orbit is a distinct musical voice. If they were all playing unrelated tunes, the result would be a deafening cacophony leading to a swift and discordant end. But through orbital resonance, their motions are harmonized into a grand celestial chord, a symphony of gravity where each participant reinforces the stability of the whole. The simulations show that such a system can easily survive for 5, 6, or even 10 billion years, more than the current age of our own solar system. This isn't a temporary truce in a gravitational war. It's a lasting peace treaty written into the very fabric of their motion. The existence of these unexpectedly stable systems forces a major shift in our understanding of stellar dynamics. It reveals that complexity does not automatically equate to fragility. Instead, it demonstrates that the universe has a natural propensity for finding stable, self-correcting configurations, even in the most crowded of gravitational environments. The initial assumption that such systems must be fleeting is rooted in our experience with simpler, unstable three-body interactions. but with 10 bodies, the sheer number of possible resonant relationships increases exponentially, offering nature a vast menu of potential stable solutions to choose from during the system's formation. It suggests that if a system forms with the right initial conditions, the right amount of spin in the original gas cloud, the right distribution of mass, it can naturally fall into one of these deeply stable resonant states and remain there for eons. This discovery provides a powerful answer to a fundamental question. If these systems are so unstable, why do we see them at all? The answer is that we are only seeing the survivors, the rare but perfectly balanced systems that have passed the ultimate test of time. They are the cosmic equivalents of a perfectly balanced mobile, where every component is in tune with every other, able to withstand the gentle breezes of external gravitational influences from passing molecular clouds or other star systems without collapsing into disarray. Finding such a system is like discovering a perfectly preserved fossil from the dawn of the galaxy, a living relic that has witnessed the vast majority of cosmic history while maintaining its exquisite and complex structure. This cosmic clockwork of resonant stability leads us to another discovery that is, in its own way, just as bewildering. We tend to think of a star system as a family of stellar siblings, all born from the same parent cloud of gas and dust at roughly the same time. They should share a common age, a shared history written in their similar compositions. But spectroscopic analysis of one particular Decuple system delivered a result so bizarre it seemed to defy logic. The stars were not all the same age. In fact, some members of this celestial family were billions of years older than their supposed brothers and sisters. It was like walking into a nursery and finding a newborn baby, a toddler, a teenager, and an elderly grandparent all claiming to be immediate siblings. This finding struck at the very heart of our standard models of star formation, which posit that stars in a bound group condense from a single, collapsing molecular cloud core over a relatively short period of cosmic time. The evidence for this multi-generational family comes from the precise language of starlight itself. Spectroscopes act as cosmic thermometers and chemical laboratories, allowing astronomers to measure a star's surface temperature, its gravity, and most importantly for dating, its chemical composition. Younger stars are typically richer in heavy elements, forged in the hearts of previous generations of stars and seeded into the interstellar medium by supernova explosions over billions of years. Older stars, by contrast, are metal-poor, composed almost entirely of the pristine hydrogen and helium that existed shortly after the Big Bang. When astronomers pointed their spectroscopes at this system, they found a staggering disparity. One group of stars showed the chemical signature of a venerable population, perhaps 10 billion years old, having formed when the galaxy itself was in its chaotic infancy. Another subgroup displayed the enriched composition of a middle-aged star of 5 billion years, and at the heart of the system, a brilliant, hot blue star shone with the telltale signs of a youthful newcomer, a mere infant at only a few 100 million years old. These stars could not possibly have been born together, so how did this impossible family come to be? The leading theory is as dramatic as it is elegant: stellar capture. This is the gravitational equivalent of a cosmic kidnapping. The original system, let's imagine it was a stable sextuple or octuple group, was likely drifting through a dense region of the galaxy, perhaps a bustling stellar nursery or a crowded globular cluster. In such a dense environment, close encounters between star systems are far more common. Billions of years ago, this original family may have had a fateful close pass with a much older, wandering binary pair of stars. As the two systems swung by each other, their complex gravitational fields interacted like a celestial slingshot. The immense pull of the core system managed to rob the passing binary of its orbital energy, effectively trapping it. Instead of continuing on their original path, the two elderly stars found themselves locked into a new, wide orbit around the younger family, becoming permanent, if unwilling, members. This process could have repeated itself over the eons, with the system acting as a gravitational sponge, soaking up solitary stars or smaller multiples it encountered, each capture event adding a new generation to the growing clan until it reached its current decuple configuration. This predatory formation method challenges the passive picture we often have of star systems simply forming in place and staying there. It paints a far more dynamic and interactive portrait of the galaxy, where stellar systems can grow and evolve by cannibalizing their neighbors. The stability of the resulting decuple system, despite its mixed origins, is a testament to the power of hierarchical organization we discussed earlier. The captured stars don't just get thrown into the chaotic center, they are typically placed into those wide, stable outer orbits of the hierarchy, where their gravitational influence is smoothed out over vast distances. This discovery fundamentally changes our understanding of what a star system is. It is not necessarily a closed, isolated family, but can be an open, accumulating collective, a product of both birth and adoption. Its history written not just in the chemistry of its stars, but in the very different ages of its members. But within these systems of 10 suns, the life cycle of a star can take on a grotesque and cyclical form of cosmic horror, giving rise to what astronomers call a zombie star. In one particularly dramatic system, observations revealed a star that was, by all rights, already dead. It was a white dwarf, the incredibly dense, Earth-sized core of a star that had long ago burned through its nuclear fuel, shed its outer layers, and faded into a hot, fading ember. This stellar corpse, however, was far from resting in peace. It was locked in a tight, frantic orbit with a living, bloated red giant companion, and from this living star, the white dwarf was actively siphoning material. A relentless stream of hydrogen gas, stolen from the outer atmosphere of the red giant, cascaded down onto the surface of the dead star. Under normal circumstances, a solitary white dwarf simply cools and dims over billions of years. But here, under the immense pressure and heat generated by this constant rain of fresh fuel, the stolen hydrogen accumulates on the white dwarf's surface, compressing and heating until it reaches a critical flashpoint. The result is not a full supernova, but a nova, a colossal, runaway thermonuclear explosion that detonates on the surface of the dead star. For a few glorious days, this stellar corpse erupts in a blaze of light, becoming tens of thousands of times brighter than our sun, outshining every other star in the decuple system before gradually fading back to its dormant state. This cycle of death, feeding, and explosive rebirth is terrifying enough on its own. But in a system with 9 other gravitational players, it becomes a uniquely twisted laboratory. The other stars in the system don't just watch this macabre dance from a distance, they actively participate in it, influencing the timing, intensity, and even the aftermath of each detonation. The complex gravitational tides from the other stellar members constantly tweak the orbit of the white dwarf and its victim. These subtle gravitational nudes can slightly alter the distance between the two stars, which in turn changes the rate at which the white dwarf feeds. A closer pass from a distant stellar sibling might compress their orbit, accelerating the flow of stolen gas and triggering a nova explosion months or years earlier than it would have occurred naturally. Conversely, a gravitational pull in the opposite direction might momentarily widen the gap, starving the zombie star and delaying its next explosive feast. This external modulation transforms the nova from a predictable clock into a chaotic timepiece, its ticks and tocks dictated by the grand gravitational orchestra of the entire system. Furthermore, the debris from the explosion itself becomes a fascinating subject of study. When the nova erupts, it blasts a shell of newly forged heavy elements and stellar material out into space at thousands of kilometers per second. In a simple binary system, this ejector would expand into a relatively symmetrical, bubble-like nebula. But in the decuple environment, the powerful radiation pressure and stellar winds from the other brilliant, hot stars immediately begin to interact with this expanding shell. They sculpt it, tear it into irregular shapes, and accelerate parts of it while slowing others, creating a complex and short-lived nebulous structure that would be impossible to form elsewhere. By studying the dynamics of this ejector, astronomers can indirectly measure the intensity of the radiation fields and stellar winds from the other stars, gaining insights into their properties that are difficult to obtain through direct observation alone. Each nova eruption becomes a temporary probe, illuminating the invisible forces at play within the system. The most profound implication of this zombie star phenomenon lies in its potential final act. With each cycle of feeding and explosion, the white dwarf does not eject all of the accumulated material. A fraction of it settles onto its surface, increasing its mass. There exists a critical threshold known as the Chandrasekhar limit, about 1.4 times the mass of our Sun. If the white dwarf's relentless feeding ever pushes it over this limit, the entire star will no longer be able to support its own immense gravity. In a fraction of a second, it will undergo a catastrophic collapse and then explode in a Type Ia supernova, a titanic detonation so brilliant it can, for a few weeks, outshine an entire galaxy. This is the true, ultimate death of the star, a finality from which no zombie can return. The presence of the other 8 stars adds a frightening variable to this doomsday scenario. Their gravitational influence could, in theory, provide the final push, destabilizing the orbit just enough to dump a critical excess of mass onto the white dwarf and triggering the supernova prematurely. This means the other stars in the system could literally be the architects of their siblings' annihilation. Studying this process in a Decuple system offers a front-row seat to the final stages of stellar evolution, providing crucial data to understand one of the most important standard candles in cosmology, the very tools we use to measure the expansion of the universe itself. While we have been exploring the visible light and radiation from these systems, there is an entirely different, invisible signature they leave on the universe, one that literally bends the fabric of reality itself. The frantic, accelerating motions of so many massive stars in such a confined space make Decuple systems veritable factories for gravitational waves. These are not waves of light or sound, but ripples in the very geometry of spacetime, first predicted by Einstein over a century ago and only directly confirmed in the last decade. Think of spacetime as a vast, still pond. A single star is like a small, stationary float on the surface, creating only a gentle, permanent dimple. But when you have multiple massive stars whirling around each other at incredible speeds, especially the tight inner binaries within a Decuple hierarchy, it's like having several heavy spinning tops on that pond's surface. Their rapid acceleration and changing gravitational fields constantly churn the water, sending out concentric ripples that propagate outward at the speed of light. In the case of a Decuple system, you don't just have one or two tops, you have a whole collection of them, all spinning at different rates and in different orientations, creating a complex, overlapping interference pattern of spacetime ripples. The key ingredient for generating strong gravitational waves is not just mass, but acceleration in a non-symmetrical way. A perfectly spherical star expanding and contracting wouldn't produce them. It's the rapid orbital motion of immense masses in tight, fast binaries that does the trick. Within a Decuple system, the innermost pairs are the prime culprits. These are often pairs of neutron stars or even stellar mass black holes that have been driven into incredibly close orbits by the system's complex dynamics, sometimes circling each other in a matter of hours. As they orbit, they lose energy by emitting gravitational waves, which causes their orbits to very slowly decay, bringing them even closer together and increasing their orbital speed in a runaway process that ends in a final, violent merger. For every such pair in the system, there is a constant, faint hum of gravitational radiation being broadcast into the cosmos. Now, multiply that by the number of tight binaries and high-mass stars in a single Decuple system, and you begin to appreciate the sheer cacophony of spacetime vibrations it can produce. This is where the next generation of astronomy comes into play. Ground-based detectors like LIGO and Virgo have opened our ears to the universe by catching the loud, transient chirps from merging black holes and neutron stars. But the persistent, lower-frequency hum from systems like these is currently beyond their hearing range. This is the mission of future space-based observatories, most notably the Laser Interferometer Space Antenna, or LISA. Scheduled for launch in the next decade, LISA will consist of 3 spacecraft flying in a vast triangular formation millions of kilometers apart, connected by lasers. Freed from the seismic noise of Earth, this colossal instrument will be exquisitely tuned to the low-frequency gravitational wave spectrum. It is within this range that the collective chorus of millions of tight binary systems throughout the galaxy, including the most extreme members of Decuple families, will create a detectable gravitational wave background. Imagine listening to an orchestra from a great distance. With LIGO, we hear the occasional loud crash of a cymbal or the boom of a bass drum from a nearby merger. But with LISA, we will be able to hear the entire string section, the continuous, resonant hum of all the binary stars in the Milky Way playing together. A single, nearby Decuple system would be a particularly loud and distinctive section within that orchestra, its unique combination of orbital frequencies creating a complex harmonic signature that LISA's sophisticated data analysis tools could potentially isolate from the galactic crowd. Detecting this background hum is more than just a technical achievement. It will provide a revolutionary new way to census the most exotic and hidden objects in our galaxy. Many of the compact objects in these systems, like solitary stellar mass black holes or quiet white dwarf binaries, are virtually invisible to traditional telescopes. But they cannot hide from gravitational waves. Their motion betrays them. By analyzing the specific frequencies and amplitudes of the waves coming from a Decuple system, astronomers will be able to weigh the invisible participants, confirm their orbital configurations, and even test general relativity in regimes of gravity that are far more extreme than anything in our solar system. It will allow us to peer into the very heart of these gravitational maelstroms and understand the final fates of the stars within them, revealing a universe that is not just seen or heard, but felt through the subtle stretching and squeezing of spacetime itself. Yet within the gravitational whirlwind of a Decuple system, not all matter is destined to become a star or a planet. In fact, a significant portion of it remains as a vast, swirling reservoir of dust and gas, and the way this material behaves is one of the most visually stunning and scientifically revealing discoveries. Using powerful infrared telescopes that can pierce through the glare of the stars to see the cooler material around them, astronomers have observed immense structured clouds of cosmic dust. But these are not the smooth, orderly protoplanetary disks we see around infant single stars, which resemble thin, elegant phonograph records. Instead, the dust in a 10-star system is sculpted into bizarre, asymmetrical forms, clumpy, disjointed rings, warped spirals, and vast, swirling arms that look more like a galaxy in miniature than a typical debris disk. This is the dust enigma, a beautiful but chaotic infrared signature that tells a story of perpetual, violent stirring. The sheer gravitational energy of 10 massive bodies constantly churns this material, preventing it from ever settling down into the calm, stable environment needed for planets to coalesce. Every time a star or a binary pair swings through its orbit, its gravity acts like a massive spoon stirring a cosmic cup of coffee, creating turbulence and density waves that ripple through the dust. These gravitational tides compress some regions into bright, dense clumps while simultaneously tearing other regions apart, creating vast voids and gaps. The resulting structures are transient and ever-changing, a celestial dance of dust that reforms itself with every orbital cycle of the stellar components. Trying to form a planet here would be like trying to build a sandcastle in the surf during a hurricane. The moment a small clump of dust and rock begins to stick together, a passing gravitational tide would rip it apart, scattering the material back into the chaotic whirlpool. This relentless stirring does more than just prevent planet formation. It creates a uniquely hostile environment through a phenomenon known as collisional fragmentation. In a calm disk, dust grains can gently collide and stick together, gradually building up to planetesimals and eventually planets. But in the turbulent maelstrom of a decuple system, particles are whipped around at incredible relative speeds. When these high-velocity dust grains and pebbles collide, they don't gently coalesce, they pulverize each other in violent impacts that generate even more fine dust. This process creates a self-perpetuating cycle of destruction, where any larger bodies that might have begun to form are constantly ground back down into microscopic particles. The system becomes a giant cosmic grinder, filled with the glittering remains of worlds that never were. This is why the dust clouds appear so bright in infrared light. They are filled with an immense amount of this fine, freshly ground dust, which is extremely efficient at absorbing the starlight and re-radiating it as heat. The beautiful, intricate spirals and rings we see are therefore not nurseries for new worlds, but their graveyards, a testament to the destructive power of complex gravity. They are the scattered ashes of planetary building blocks, forever trapped in a cycle of assembly and disintegration. The specific shapes of these dust structures act as a direct map of the hidden gravitational forces at play. A tight, bright ring at a specific distance from the system's center might betray the orbital radius of a particular stellar binary, whose gravity acts as a shepherd, clearing a gap in the dust much like Saturn's moons sculpt the rings of Saturn. A lopsided, banana-shaped arc of dust could be a telltale sign of a recent close encounter between two of the stars, a gravitational wake left in the dusty medium. By carefully modeling these intricate dust patterns, astronomers can actually infer the presence and orbits of stars that are otherwise too dim or too close to their bright companions to be seen directly. The dust becomes a luminous screen upon which the invisible ballet of gravity is projected, allowing scientists to reverse engineer the complex dynamics of the entire system. It is a form of cosmic forensics where the scattered debris at the scene tells the story of the gravitational interactions that put it there. Each strange loop and clump is a clue, helping to piece together the complete orbital puzzle of all 10 stellar components. Ultimately, the chaotic dust clouds of a decuple system represent a state of permanent cosmic adolescence. While most star systems eventually clear their dusty disks, either by forming planets or by having the dust blown away by stellar radiation, these extreme families never get that chance. The gravitational turbulence is a constant, never allowing the dust to either fully coalesce or fully disperse. The system remains forever young in a dynamical sense, trapped in a protracted and violent childhood that may last for the entire lifetime of its stars. The beautiful, swirling infrared nebulae are therefore a portrait of arrested development, a snapshot of perpetual chaos that is both destructive and creatively magnificent, showing us a side of stellar evolution where the peaceful formation of planets is an impossible dream, replaced by an endless, dazzling storm of dust. Yet, amid the gravitational turmoil and the threat of stellar violence, nature occasionally carves out a brief and spectacular refuge, a place where the conditions for life are not just possible, but are offered by multiple stars in a fleeting moment of cosmic alignment. This leads us to a theoretical but profoundly plausible discovery, a decuple system where the circumstellar habitable zones of several stars briefly intersect. In such a system, the standard concept of a single, stable, Goldilocks region is completely reimagined. Instead, imagine a specific, transitory volume of space where the orbits of a planet and its multiple suns align just so, allowing it to pass through the life-friendly zones of not one, but several different stars in succession. This isn't a permanent, placid orbit, it's a periodic pilgrimage through a series of overlapping oases in a stellar desert. For a world on a vast, chaotic path, this intersecting region would be a haven, a place where it could, for a time, experience conditions not totally dissimilar to Earth. The light cycle on such a world would be a spectacle beyond human comprehension. There would be periods of multiple daylight where 2 or even 3 suns of different colors and intensities hang in the sky, casting a complex and shifting palette of shadows. A deep blue-white giant might dominate the heavens, while a smaller orange sun and a faint red companion trace slower arcs across the firmament. Sunrises and sunsets would be multi-stage events, a slow symphony of light as one star dips below the horizon while another is still ascending, creating extended periods of twilight that could last for days or even weeks. The very definition of day and night would lose all meaning, replaced by an unpredictable rhythm of illumination dictated by the complex gravitational dance of its 10 stellar hosts. The potential for life in such a variable environment is a thrilling puzzle for astrobiologists. The primary challenge is the incredible fluctuation in energy received. The planet would cycle through extremes, from the blistering intensity of proximity to a hot, massive star to the dim, cool glow of a red dwarf. Life would need to be phenomenally adaptable, not just to seasonal changes, but to fundamental shifts in the baseline climate. The most plausible scenario would be a life form that is highly opportunistic and resilient, perhaps with the ability to enter states of dormancy or cryptobiosis during the harsh transitions between stellar influences. Think of the extremophiles on Earth, like tardigrades that can survive the vacuum of space, or bacteria living in boiling hot springs and frozen tundra. Now imagine a planetary biosphere where such extreme adaptability is not the exception, but the absolute rule for survival. The biochemistry of life here might be incredibly versatile, relying on metabolic pathways that can function across a wide temperature range, or organisms that can rapidly alter their pigmentation to cope with different spectra of stellar radiation. The very pace of evolution would be accelerated, driven by the relentless environmental pressure to adapt or face extinction with every orbital cycle. This wouldn't be a world with a stable, gradually evolving ecosystem like Earth's. It would be a planet in a constant state of ecological upheaval and rapid succession, where biological niches open and close with the rhythmic passing of its many suns. However, this astrobiological potential is haunted by a cruel paradox. The very gravitational forces that create this rare and beautiful orbital intersection are also the ones that ensure it cannot last. The region of overlapping habitable zones is not a stable, stationary volume. It is a moving target, a fleeting convergence of conditions that exists only because of the precise, momentary alignment of the stars in their complex dance. The planet's path through this sanctuary is temporary. Its chaotic orbit will inevitably carry it away, plunging it back into the more common and hostile states of the system, either swinging inward to be scorched by a close-passing star or drifting outward into a deep, perpetual freeze. The window for life to arise and establish itself is therefore terrifyingly narrow on a cosmic timescale. It suggests that if life does exist in such a place, it may be inherently transient, a brilliant but short-lived flash of biology in the void, forever at the mercy of celestial mechanics. This discovery forces us to confront a profound question. Is the potential for life a matter of stable, long-term nurturing, or can it be a spark that ignites repeatedly in brief, favorable moments, only to be extinguished and perhaps rekindled later in a planet's long journey? The overlapping habitable zone is not a promised land, but a series of waste stations, offering a glimpse of a universe where life, against all odds, might find a way to persist in the most temporary and precarious of sanctuaries. While the resonant stability of some systems offers a glimpse of cosmic harmony, others showcase the raw, untamed power of gravity to accelerate matter to velocities that border on the unbelievable. This brings us to a record-breaking discovery within one of these stellar families, a star moving so fast it challenges our very understanding of motion. Designated as part of a system we will call S271, observations confirmed that one particular stellar member, a compact and massive object, does not trace a sedate elliptical path. Instead, its orbit is an incredibly stretched-out needle, a hyperbola in all but name, that brings it screaming into the inner system before hurling it back out to an immense distance. At the precise moment of its closest approach to the system's central gravitational powerhouse, likely a tight cluster of several massive stars, this stellar bullet reaches a velocity so immense it has been clocked at a significant fraction of the speed of light. We are not talking about thousands of kilometers per second, but a substantial percentage of the universe's ultimate speed limit. The mechanism behind this incredible acceleration is a gravitational slingshot of unrivaled ferocity. As the star falls inward, it trades gravitational potential energy for kinetic energy, picking up speed like a stone dropped from a skyscraper. But in this case, the skyscraper is the combined gravitational well of multiple stellar giants, and the slingshot maneuver is exquisitely tuned by the complex dance of all the other stars in the system. Their combined gravity doesn't just let the star fall. It focuses and channels its descent, ensuring it swings past the central mass with a precise trajectory that imparts the maximum possible acceleration. A natural and infinitely more powerful version of the gravity assists we use to propel our spacecraft across the solar system. The consequences of moving at such a relativistic velocity are not merely about breaking speed records. They fundamentally alter the star's appearance and the very physics that govern it. According to Einstein's theory of special relativity, as an object approaches the speed of light, strange things begin to happen from the perspective of a distant observer. The first effect is a dramatic increase in mass. While the star's rest mass remains the same, its effective mass from a dynamic standpoint balloons, requiring ever more energy to accelerate it further. This effect alone places a natural brake on its velocity, preventing it from ever actually reaching light speed. The second, more visually striking effect is relativistic aberration and Doppler shifting. The light emitted by the star as it rockets towards us is not just brightened, it is brutally compressed. All of its radiation, the visible light, the ultraviolet, the X-rays, is squeezed into shorter, more energetic wavelengths. To our telescopes, the star would undergo an extreme version of a Doppler shift, its color blazing an intense, unnatural blue as it approaches, and then, as it recedes, its light would be stretched into long, faint, deep red waves, a ghost of its former brilliance. If you could somehow watch this star during its close pass, it would appear to be rotating in slow motion due to an effect called relativistic time dilation. The processes on its surface, the churning of its plasma, even the flicker of its magnetic fields, would seem to crawl from our external reference frame, while for the star itself, time would pass at its normal rate. This stellar projectile does more than just demonstrate esoteric physics. It transforms the space around it into the most powerful natural particle accelerator in the known universe. The space surrounding stars is not a perfect vacuum. It is filled with their powerful stellar winds, a constant stream of charged particles, protons and electrons blowing outward into the system. When our relativistic star plows through this environment at near light speed, it behaves less like a celestial body and more like a cosmic bulldozer hitting a sea of subatomic sand. The charged particles in its path don't just gently move aside, they are caught by the star's own magnetic field and the immense shock front it generates. These particles become trapped and are whipped around in the turbulent wake, gaining tremendous energy with each pass. This process, known as Fermi acceleration, can boost these mundane stellar wind particles to energies that dwarf anything produced by our most powerful human-built atom smashers like the Large Hadron Collider. The result is a furious torrent of high-energy cosmic rays and gamma radiation that floods the entire system each time this star makes its close pass. For any hypothetical planets in the vicinity, This periodic blast of radiation would be an extinction-level event on a scale we can barely conceive, a wave of fundamental particles so energetic they would pierce through planetary crusts and shatter complex molecules, rendering the inner regions of the system utterly sterile for the duration of the flyby. The existence of such a star serves as a stark reminder of the incredible energies locked within gravitational fields. We often think of particle accelerators as sprawling, technological marvels built by intelligent life. Yet here, the simple, mindless application of gravity, orchestrated across 10 massive bodies, can achieve the same result on a far grander and more terrifying scale. It shows us that the universe is already performing the most extreme experiments in high-energy physics, and all we have to do is look in the right places to witness them. This natural accelerator provides a unique laboratory for studying physics under conditions we could never hope to recreate on Earth, offering insights into the behavior of matter and radiation at energies that existed only in the very first moments after the Big Bang. One of the most alluring and unexpected treasures found within these stellar families has to do with their very composition. When astronomers analyze the light from a star, they can break it down into a spectrum, a chemical fingerprint that reveals exactly what elements are present in that star's atmosphere. In a handful of these Decuple systems, this cosmic fingerprint has revealed a startling anomaly, a spectacular overabundance of the heaviest and most precious elements in the universe. We're talking about elements like gold, platinum, and even uranium, appearing in concentrations that are tens or even hundreds of times greater than what is found in our own sun or in typical isolated stars. This isn't a slight enrichment, it's a cosmic gold rush, a level of wealth that seems to defy the standard processes of stellar nucleosynthesis. After all, a star's internal furnace is excellent at cooking up lighter elements like carbon, oxygen, and silicon, but it takes something far more cataclysmic to forge the heaviest atoms. A regular star, even one that goes supernova, cannot produce the immense neutron flux required to create a significant amount of gold or platinum. So how did these stellar families become the billionaires of the galaxy, hoarding fortunes in heavy elements? The cosmic alchemist responsible for this incredible wealth is one of the most violent and energetic events known, the merger of two neutron stars. Picture the aftermath of two supernova explosions, each leaving behind an ultra-dense, city-sized core made almost entirely of neutrons, spinning rapidly and possessing a ferocious magnetic field. If these two remnants are locked in a binary orbit, they will slowly spiral inward over billions of years, losing energy in the form of gravitational waves until they finally collide. The moment of their merger is one of pure, unadulterated cosmic violence. It unleashes a blinding flash of gamma rays and, in the process, creates conditions so extreme that it becomes a factory for the rapid neutron capture process, or the R process. In this frenzied environment, atomic nuclei are bombarded by a tsunami of free neutrons, allowing them to grow astronomically in mass in a matter of seconds, climbing up the periodic table to form the heaviest stable elements like gold, platinum, and the radioactive actinides like uranium and thorium. The collision then blasts these newly forged precious metals out into space at relativistic speeds, seeding the surrounding interstellar medium with a cloud of cosmic treasure. This is where the unique gravitational architecture of a Decuple system becomes a crucial advantage. An isolated star like our Sun drifts through the galaxy largely on its own. The chance of it passing directly through the relatively small and fast-expanding debris cloud from a neutron star merger is infinitesimally small. It would be like winning the cosmic lottery. But a Decuple system is a different beast entirely. Its immense collective gravity gives it a far more effective net for catching this material. The system's complex, multi-layered gravitational field creates a much larger effective cross-section, a wider target for intercepting these rare and valuable clouds of ejected material. Think of it like fishing. A solitary star is a single fishing line with one hook, hoping for a lucky catch. A decuple system, with its 10 massive stars and their extensive sphere of gravitational influence, is more like a colossal trawler net, sweeping through a vast volume of space and dramatically increasing its chances of ensnaring the enriched debris from a nearby neutron star merger. Furthermore, the system's own violent history of stellar interactions and supernova means it was likely home to the very neutron stars that merged in the first place. The system isn't just a passive collector, but can be the very foundry where these elements are created, ensuring the resulting wealth is kept within the family. Once this cloud of gold and platinum dust is captured, the process of enrichment begins. The fine particles and gas, now gravitationally bound to the system, will slowly spiral inward over time, accreting onto the surfaces of the individual stars. This is not a gentle rain, but a steady influx of the universe's most exotic elements, painting the stellar atmospheres with a signature of incredible cosmic fortune. We see this directly in their spectra, where the absorption lines for these heavy elements are strikingly prominent. This discovery does more than just explain a chemical curiosity. It provides a powerful new method for tracing the history of the most extreme cosmic events. When we find a star with a spectacular overabundance of R-process elements, it is direct forensic evidence that a neutron-star merger occurred in its relative vicinity, and that the star's home system was gravitationally robust enough to capture the spoils. It turns these decuple systems into living archives, their stellar atmospheres acting as permanent records of the most titanic explosions to have shaken that corner of the galaxy, perhaps billions of years ago. Their immense wealth is a direct testament to a violent and glorious past, a story of cosmic death and rebirth written in the language of gold and starlight. Imagine trying to study the true nature of a single person in a crowd, but every time you look, a different set of blinding spotlights is either shining directly on them or casting them into deep shadow, completely altering their appearance. This is the maddening challenge astronomers face with a particular type of star found in these systems, a celestial chameleon whose observed properties seem to shift and morph in an impossible way. In one observation, this star appears as a brilliant, hot blue giant, blazing with fierce ultraviolet light. A few months later, the same star seems to have transformed into a much cooler, calmer yellow star. And then, later still, it might register as a dim, ruddy red giant, only to cycle back again. The star itself isn't physically changing its fundamental nature at this frantic pace. Instead, it is the victim, or the beneficiary of a perpetual cosmic light show orchestrated by its 9 stellar companions. From our fixed vantage point on Earth, our line of sight to this star is constantly being manipulated by the intricate orbital dance of the entire system. The primary reason for its chameleon-like behavior is a relentless series of stellar eclipses. Because the system's orbital plane is roughly aligned with our viewpoint, the stars are constantly passing in front of and behind one another. When a tremendously luminous hot O-type star moves directly behind our target star from our perspective, the target isn't dimmed, it is illuminated. The intense blue-white light from the O-type giant reflects off the atmosphere and any surrounding dust of the chameleon star, making it appear far hotter, bluer, and more luminous than it truly is. It's like holding a faint light bulb in front of a powerful searchlight. The bulb itself doesn't change, but it appears to glow with an intense, borrowed brilliance. Conversely, when a large, cooler red giant passes in front of it, the chameleon star is not only eclipsed and dimmed, but it is also bathed in the red giant's deep crimson light. Its own spectrum becomes contaminated with this cooler signature, causing its measured color temperature to plummet and making it mimic the properties of a much older, redder star. The sheer number of stellar light sources ensures this cycle of spectral impersonation is endlessly complex and unpredictable. This stellar identity crisis creates a monumental puzzle for astronomers trying to determine the star's true characteristics. Is it a massive star or a medium mass star? Is it young or old? The answers to these basic questions remain frustratingly out of reach because the light we receive is never purely its own. It's a composite signal, a messy cocktail of direct light from the chameleon star, reflected light from its brighter siblings, and absorbed light when it is eclipsed by larger companions. Untangling this knot requires more than just patience. It demands sophisticated computer modeling that can simulate the precise positions, luminosities, and colors of all 10 stars in the system across their entire orbital history. Astronomers must essentially create a digital twin of the entire Decuple system and run the clock forward and backward, testing thousands of different configurations for the chameleon star until they find one set of true properties that, when combined with the light pollution from the other 9 stars, perfectly reproduces the bizarre and shifting observations. This process is like trying to determine the true color of a single chameleon by only ever looking at it through a kaleidoscope made of 9 other, differently colored chameleons. The difficulty is compounded by the fact that some of the most crucial data comes during the brief, precious moments of a clean transit, when the chameleon star passes in front of a star of known, stable properties. During these fleeting events, astronomers can use the background star as a backlight to probe the chameleon star's atmosphere in silhouette, momentarily isolating its fingerprint from the overwhelming glare of the system. It is a painstaking, years-long endeavor of celestial detective work, where the mystery is not a hidden object, but the true face of an object that is constantly being masked by its own family. While the spectacle of multiple suns and relativistic stars is breathtaking, the true scientific treasure of a Decuple system lies in its profound ability to test the very foundations of our understanding of gravity. Einstein's theory of general relativity, which describes gravity not as a force but as the curvature of spacetime by mass, has passed every test thrown at it for over a century. But most of those tests, like the bending of starlight by our sun, occur in what physicists call the weak field regime, where gravity is relatively mild. A Decuple system, with its dense clusters of massive stars orbiting at breakneck speeds, catapults us directly into the strong field regime, offering a natural laboratory of unrivaled precision. Here, the curvature of spacetime isn't a subtle effect. It is a dominant, dramatic force that dictates the motion of entire stars. The most stunning confirmation of this comes not from exotic particles or invisible waves, but from the simple, patient act of timing, watching the clockwork of stellar eclipses with an accuracy that borders on the obsessive. Consider a tight binary pair of neutron stars at the heart of such a system, whirling around each other in a frantic dance completed in just a few hours. According to Newtonian gravity, their orbit should be a static, unchanging ellipse, like a track a runner circles again and again. But general relativity predicts that this orbit itself is in motion. The immense mass and velocity of the stars cause the very fabric of spacetime to warp so severely that the point of closest approach, known as the periastron, cannot stay in one place. Instead, it slowly rotates or precesses around the stars, tracing out a beautiful, rosette-like pattern over time. This is not a small effect. In our solar system, the precession of Mercury's orbit is a tiny 43 arcseconds per century, a subtle drift that took centuries to detect. In a relativistic binary within a Decuple system, the precession can be absolutely massive, amounting to several degrees per year. This creates a directly observable phenomenon. The timing of the stars' eclipses of one another changes in a predictable yet dramatic way. Astronomers meticulously record the moments when one star passes in front of the other, causing a dip in the system's combined light. In a simple Newtonian universe, these eclipses would occur with metronomic regularity. But in the relativistic reality of this system, each successive eclipse arrives slightly early or late compared to the last, following a pattern that precisely matches the prediction of a spiraling, precessing orbit. The accumulated data over years of observation produces a graph that is a direct fingerprint of curved spacetime. The deviations from perfect timing, measured to within a fraction of a millisecond, align with Einstein's equations with an accuracy far beyond what is possible to achieve in our own much calmer solar system. This is because the gravitational hills and valleys these stars move through are exponentially steeper and deeper. It's the difference between testing the aerodynamics of a paper airplane in a gentle breeze and testing a supersonic jet in a hurricane. The extreme conditions magnify the effects, making them unmistakable and allowing for measurements of unparalleled precision. This celestial laboratory also provides a pristine test for another key prediction: gravitational redshift. When light climbs out of a powerful gravitational field, it loses energy, causing its wavelength to stretch towards the red end of the spectrum. On Earth, this is a minuscule effect, difficult to measure even with our most sensitive instruments. But in a Decuple system, when one of the stars in a tight binary is a super-dense neutron star, the effect is magnified tremendously. As the neutron star moves in its orbit, its light is periodically climbing out of the deep gravitational well of its massive companion. During this phase of its orbit, astronomers can measure a significant redshift in its spectral lines, a shift that then diminishes as the star moves to a part of its orbit where the gravitational pull is less extreme. The consistency of this shifting with the orbital phase provides yet another independent and robust confirmation that gravity does indeed stretch the very fabric of space and time, affecting the light that travels through it. The Decuple system, with its multiple pairs of stars at various separations and masses, offers not just one, but a whole suite of such tests, allowing scientists to verify general relativity across a range of conditions, all within a single, coherent gravitational environment. It transforms an abstract theory of physics into a tangible, observable reality, written in the motion of suns and the precise ticking of a cosmic clock. Deep in the blackness of interstellar space, far from the comforting glow of any stellar neighbor, speeds a solitary runaway, a massive, brilliant star fleeing its birthplace at a velocity so great it will never return. For years, this stellar fugitive was a mystery, a lone wolf whose origins were lost to the void. But by employing the cosmic equivalent of forensic science, astronomers did something extraordinary. They traced the star's path backwards through time and space, and its trajectory led them, like a perfectly straight line drawn across the galaxy, directly back to the chaotic gravitational heart of a known Decuple system. This runaway star was not born in isolation. It was violently evicted from the most crowded of stellar apartments, a victim of a gravitational game of pool played with stellar mass billiard balls. The mechanism for this spectacular ejection is one of the most dramatic processes in orbital mechanics, a multi-body gravitational slingshot. Within the densely packed core of a Decuple system, where multiple tight binaries whirl around each other, the stability of the hierarchy is always provisional. Occasionally, a star in a wider orbit will make a close pass by one of these central binary pairs. As it swings by, it transfers a tremendous amount of its own orbital energy to one of the stars in the binary through gravity alone. Think of it as a celestial crack of the whip. The incoming star gets a gravitational tug that slows it down and binds it more tightly to the system, but in exchange, the star in the binary that received the energy gets a ferocious kick. Its velocity is boosted so dramatically that it reaches or even exceeds the system's escape velocity, the speed required to break free from the collective gravitational pull of its 9 siblings. In an instant, that star is no longer a member of a family. It becomes an interstellar castaway hurled out into the galactic darkness on a one-way journey. The sheer speed of these ejections is staggering, often reaching hundreds of kilometers per second, fast enough to cross the distance from the Earth to the Moon in under an hour. This process effectively turns the Decuple system into a natural particle accelerator, using gravity itself as the launching mechanism. The discovery of this runaway's origin story does more than just solve a single mystery. It reshapes our understanding of how massive stars are distributed throughout the galaxy. We once imagined that huge, hot O-type stars, which live fast and die young, would almost always be found in the dense clusters where they were born, as they simply don't have enough time to wander far. The existence of these high-velocity runaways, now conclusively linked to their Decuple system origins, proves that the galaxy is a much more dynamic and violent place. These stellar catapults can fling these brilliant giants clear of their birth clouds, seeding different regions of the galaxy with massive stars and the heavy elements they create. A runaway star becomes a solo ambassador of its former home, carrying the unique chemical signature of its complex birthplace across vast distances. Its eventual supernova explosion will therefore occur far from its siblings, dispersing its enriched debris into a different part of the interstellar medium and influencing the chemical evolution of the galaxy in a way that would be impossible if it had remained peacefully in its cradle. This changes the narrative of stellar life cycles, showing that a star's journey can be one of dramatic exile, and that the most luminous and influential stars in the galaxy may often be those that were violently rejected from the most extreme of families. As we push our telescopes to observe the universe in the most energetic forms of light, a startling pattern emerges from these crowded stellar families. Many Decuple systems aren't just visual spectacles, they are some of the most powerful and perplexing sources of high-energy radiation in the entire galaxy, blazing with X-rays and gamma rays that defy simple explanation. These emissions are not the gentle warmth of starlight, they are the signature of matter and energy pushed to their absolute limits, and their intensity points to violent processes unfolding within the gravitational turmoil. The leading theory for this relentless high-energy output points to a truly colossal phenomenon, the constant supersonic collision of stellar winds. Within these systems, the most massive stars, the brilliant O-type and Wolf-Rayet giants, are cosmic powerhouses that do more than just shine. They blast their surroundings with a perpetual gale of charged particles, a stellar wind that streams outward at millions of kilometers per hour. In a solitary setting, this wind simply expands into the void, but in a Decuple system, these gales from multiple stars are forced to interact. Imagine 2, 3, or even 4 hurricane-force jets of plasma, each one powerful enough to strip a planet of its atmosphere, slamming into one another head-on. Where these winds meet, they cannot simply pass through each other. Instead, they create a standing shock front, a titanic wall of superheated and compressed gas glowing at temperatures of tens of millions of degrees. At these incredible temperatures, the gas doesn't just glow with visible light. It emits a flood of penetrating X-rays, turning the entire region between the stars into a vast, diffuse X-ray furnace. This isn't a rare event, it's a permanent feature of the system's environment, a continuous cosmic demolition derby that bathes the entire stellar family in a dangerous, high-energy glow. Yet the production of X-rays is only part of the story. These colliding shock fronts do something even more extraordinary. They act as nature's most efficient particle accelerators. The chaotic, magnetized boundaries where the winds collide can trap protons and electrons, whipping them back and forth across the shock front. With each crossing, the particles gain a burst of speed, a process that can eventually boost them to velocities approaching the speed of light. When these relativistic particles finally escape or collide with other particles, they release their immense energy in the form of even more penetrating gamma-ray photons. This mechanism effectively turns the entire Decuple system into a colossal, natural version of a particle collider, generating a persistent background of the most energetic radiation the universe can produce. The sheer number of potential wind collisions in a 10-star system, each with its own unique speed, density, and direction, creates a complex and overlapping web of these high-energy sources. The resulting emission isn't a steady hum. It's a fluctuating, chaotic roar of X-rays and gamma rays that varies as the stars move along their orbits and the geometry of their colliding winds constantly changes. But colliding winds are not the only engine at work. A second, more focused process contributes to the high-energy spectacle: enhanced accretion onto compact objects. We've already discussed how the system's gravity can lead to mass transfer between stars, but this same perturbing gravity has a profound effect on the behavior of any neutron stars or black holes within the family. A solitary neutron star in a quiet region of space might only occasionally flare up if a passing cloud of gas drifts too close. In a decuple system, however, the neutron star is living in a target-rich environment. The powerful gravitational tugs from the other 9 stars constantly stir the pot, perturbing the orbits of nearby objects and funneling streams of gas from stellar winds and circumstellar debris directly toward the compact object. This ensures a much more steady and violent diet of infalling material for the neutron star or black hole. As this gas spirals down at near light speed onto the object's surface or into its accretion disk, it is compressed and heated to such an extreme degree that it emits a fierce, focused beam of X-rays. In a comma system, this might be a faint and intermittent signal. Here, it is a brilliant, relentless beacon, amplified by the relentless gravitational engineering of its stellar siblings. The combination of these two processes, the diffuse, system-wide X-ray glow from colliding winds and the brilliant, pinpoint X-ray flares from enhanced accretion, creates a high-energy fingerprint that is uniquely characteristic of these most extreme and densely populated stellar environments. After centuries of observing the mature, stable survivors of the decuple population, astronomers have now achieved something once thought impossible. They have captured a direct snapshot of one of these incredible systems in the very act of being born. Deep within a roiling, luminous stellar nursery known as the Dragon's Egg Nebula, a chaotic and magnificent construction site is unfolding, revealing the violent and fragmented origins of a 10-star family. This is not a serene, gentle birth. It is a scene of cosmic pandemonium on a scale that is almost impossible to process. At the heart of this maelstrom lies a single, monstrously large cloud of gas and dust, so immense that its own gravity has caused it to catastrophically fragment, not into 2 or 3 pieces, but into a whole litter of dense, collapsing cores. Each of these cores is a stellar womb, a concentrated knot of matter destined to become one of the system's 10 suns. The entire structure resembles a vast, intricate spiderweb spun from shimmering filaments of cold molecular gas, all converging towards the central hubs where the infant protostars are rapidly taking shape. These filaments are the cosmic umbilical cords, channeling fresh material from the outer reservoir of the nebula directly down onto the growing stars in a continuous, chaotic downpour. The observations, made with radio and infrared telescopes that can peer through the obscuring dust, show a scene of breathtaking dynamism. Brilliant jets of material, launched at near relativistic speeds from the magnetic poles of the nascent stars, punch through the surrounding gas in opposing directions, creating bow shocks that glow with the heat of their creation. These outflows are the protostar's way of shedding excess angular momentum, a necessary process to allow more gas to fall onto their surfaces. They crisscross the nebula in a tangled, violent lattice, their collisions creating pockets of intensely heated gas and triggering secondary waves of star formation in the surrounding cloud. It is a self-perpetuating cycle of creation and destruction, where the birth of one star directly influences the birth of its siblings, all bound together from their very first moments. Within this turbulent construction zone, the building blocks of the future hierarchy are already clearly visible. The system is not condensing as 10 individual stars randomly scattered. Instead, the fragmentation process itself has a distinct structure. Tight groupings of 2 or 3 protostellar cores are forming exceptionally close to one another, separated by distances smaller than the orbit of Pluto in our own solar system. These are the nascent binary and triple systems, the fundamental pairs that will become the innermost dancers in the future hierarchy. Orbital motion has already begun, with spectroscopic measurements revealing that these embryonic pairs are slowly revolving around each other even as they continue to gorge on the infalling material from their shared filament. Slightly further out, other small clusters of protostars are condensing, destined to become the wider quadruple and octuple subsystems. The entire assembly appears to be a nested cradle from the very start, with gravity ensuring that the stars form in the precise layered configuration required for long-term stability. The sheer density of this protostellar cluster is staggering. If you were to stand on a hypothetical planet forming around one of these infant suns, the sky would be filled not with a single sun, but with the brilliant, chaotic glow of a dozen other nascent stars, all closer to you than the nearest star is to our sun. The night, as we know it, would not exist. This dense packing is crucial for the system's future, as it allows for the complex gravitational interactions that will eventually lock the orbits into resonant stability, or conversely, fling a star out as a runaway. Perhaps the most astonishing detail in this real-time portrait is the presence of intricate, though tumultuous, protoplanetary disks encircling many of the individual protostars. The traditional image of a planet-forming disk is a smooth, flat, rotating platter, like a celestial vinyl record. Here, the disks are anything but calm. They are warped, twisted, and violently disturbed by the relentless gravitational tides from their many stellar neighbors. A disk around one protostar might be stretched into a long, elliptical shape by the pull of a nearby sibling, while another might be truncated entirely, its outer material stripped away and stolen by a passing core. In some cases, the gravitational interactions are so strong that they create spiral density waves within the disk's luminous arms of concentrated dust and gas that spiral inward like a cosmic whirlpool. These waves act as rapid transport mechanisms, funneling material from the outer disk directly down onto the growing protostar at the center, accelerating its growth in sudden, violent bursts. The very idea of planet formation in this environment seems like a paradox. While the raw material for planets is abundant, the constant gravitational stirring makes it nearly impossible for dust grains to gently coalesce into pebbles and pebbles into planetesimals. Any fledgling planetesimal that does manage to form is just as likely to be thrown into a collision course with its parent star, or ejected from the system entirely, as it is to safely grow into a mature world. This snapshot reveals that the chaotic environment we observe in mature Decuple systems is not a later development. It is the foundational state, the crucible from which these complex families emerge. The system is being forged in fire and chaos, its future dynamics written into its DNA from the very first moments of collapse, a breathtaking confirmation that the universe's most complex architectures are born from the most turbulent of beginnings. Of all the bizarre celestial scenes a Decuple system could offer, perhaps none is more poetically stunning than the concept of a planet orbiting not one, but two of its suns at once, creating a permanent double sunset for any potential inhabitants. This is no longer just science fiction. Astronomers have identified a strong candidate for exactly this kind of world, a circumbinary planet, nestled within the complex gravitational web of a 10-star family. Think of the iconic view from Luke Skywalker's home world of Tatooine, and then amplify it to an almost unimaginable degree. On this candidate world, the primary sky would be dominated by a central pair of stars locked in their own intimate dance, the two suns orbiting each other so closely they might appear almost as a single, elongated source of light. But that's just the beginning. Further out, the other 8 stars of the system would also be visible, not as faint points of light, but as truly sun-sized disks, each a different color and brightness. Some would be brilliant blue-white pinpricks, others swollen orange or red orbs, all tracing slow, complex arcs across the heavens. There would be times when 3 or even 4 suns are above the horizon simultaneously, casting a tangled web of shifting, multi-colored shadows. True night would be a rare and fleeting event, occurring only when the planet's orbit carries it into a precise alignment where all the stellar bodies are below the local horizon at once, revealing a starfield utterly alien to our own. Confirming the existence of such a world, however, is one of the most formidable technical challenges in modern astronomy. The primary method used to find most exoplanets is the transit method, where we detect the minuscule dip in a star's brightness as a planet passes in front of it. In a simple, single star system, this is difficult enough, but in a decuple system, the light curve, the graph of the star's brightness over time, is a chaotic mess of dips and flares. The 10 stars are constantly eclipsing and occulting one another, their mutual transits creating a bewildering pattern of dimming and brightening that occurs on timescales from hours to years. Trying to find the signature of a tiny, Earth-sized or even Jupiter-sized planet within that stellar cacophony is like trying to hear a single, soft whisper in the middle of a heavy metal concert. The planet's transit signal is thousands of times smaller than the dips caused by even the smallest stellar eclipses. To make matters worse, the planet's orbit is not around a single, stable point. It must trace a wide path around the center of mass of its 2 parent stars, which are themselves whirling around each other. This means the timing, duration, and depth of the planet's transits are wildly variable. Sometimes it might transit both stars in quick succession. Other times it might only pass in front of one, and the intervals between these detectable events can be irregular and long. Astronomers must employ sophisticated computer algorithms that can model the complex gravitational interactions of all 10 stars, predict the precise timing of every possible stellar eclipse, and then subtract that overwhelming signal from the data. Only after this Herculean computational effort can they even begin to search for the faint, residual flicker that might betray the presence of a world. It is a testament to human ingenuity that we can even attempt to find a needle in such a complex and dynamic haystack. The mere possibility of this Tatooine-like world carries profound implications for our understanding of planetary formation. The standard model suggests that planets form in calm, placid disks of gas and dust around a young star. A circumbinary planet must form in a disk that encircles 2 stars, a much more turbulent and dynamically hostile environment. The gravitational pull of the 2 central stars creates a large central cavity in the protoplanetary disk, clearing out material close in and effectively creating a donut-shaped ring of debris. Within this ring, the process of planet formation is a frantic race against time and gravity. The competing tugs from the 2 stars stir up the planetesimals, causing them to collide at much higher velocities than in a single star system. These impacts are more likely to be destructive, shattering fledgling worlds rather than allowing them to gently coalesce. For a planet to form here, it must either form incredibly quickly before the gravitational stirring can grind everything to dust, or it must form much further out in the disk where the stellar influences are weaker, and then migrate inward to its current orbit. The existence of a circumbinary planet, especially within the added chaos of a decuple system, suggests that planet formation is an incredibly robust and tenacious process. It shows that the initial conditions in a protoplanetary disk can be far more violent and disruptive than we once believed, and yet the universal drive for matter to clump together under gravity can still win out. This candidate world would be a symbol of cosmic resilience, proving that planets can emerge from the most tumultuous of cradles. If this planet does exist, its long-term climate and geology would be shaped by forces we can barely imagine. The energy it receives from its 2 suns would not be constant. As the planet and its binary stars move along their respective orbits, the distance between the planet and each star would change constantly, leading to wild swings in stellar insolation. There would be seasons, but not like our own. A year on this world would be defined by its orbit around the binary center, but superimposed on that would be the much shorter months defined by the orbital period of the 2 stars around each other. When the two stars are close together in the sky, the planet would experience a blistering double summer. When they are on opposite sides of their orbit, the heating would be more moderate, but the light cycle would be one of near perpetual daylight, with one star rising as the other sets. The gravitational stresses on the planet itself would be immense. The constantly shifting tidal forces from its two suns would likely knead the planet's interior, potentially driving extreme volcanic activity far beyond anything seen on Jupiter's moon Io. This could lead to a world with a continuously resurfaced crust, a young-looking geology atop an ancient world, with towering volcanoes constantly spewing gas and ash into an atmosphere buffeted by the intense stellar winds from two different stars. The very concept of a stable, life-friendly climate seems almost impossible here, and yet the discovery of such a world forces us to expand our imagination. It presents the ultimate test for the adaptability of life, suggesting that if a biosphere could take hold at all, it would have to be one of profound and constant transformation, a life form that doesn't just endure change, but expects it as the fundamental rule of existence. But the gravitational forces that shape these systems are only half the story. Beyond the visible dance of orbital mechanics lies an invisible architecture of pure energy, a hidden web woven from the most powerful magnetic fields in the universe. When astronomers turned their most sensitive instruments toward the radio and X-ray emissions from these stellar families, they uncovered a phenomenon of staggering complexity. The magnetic fields of stars in close binaries don't just exist alongside each other. They can become dynamically entangled, weaving together into a single, system-wide structure of force. Imagine taking the most powerful bar magnet you can conceive, one that stretches millions of kilometers, and then interlacing it with 9 other magnets of similar scale, all while they whirl around one another at fantastic speeds. This isn't a static net. It's a living, breathing, and often violently snapping lattice of magnetic energy that connects all 10 stars in a continuous, energetic circuit. The process begins with the stars themselves. Many stars, especially the hot, massive, and rapidly rotating types common in these systems, generate ferocious magnetic fields through the dynamo action of churning plasma in their interiors. In a simple binary, when two such magnetized stars orbit closely, their individual magnetic fields are forced to interact. They don't just push each other aside. Under the right conditions, they can undergo magnetic reconnection, a process where the field lines break and then reconnect, effectively tying the magnetic atmospheres of the two stars together. This creates a magnetic bridge, a conduit of immense energy that allows charged particles to flow directly from one star to the other. Now, scale this concept up to a decuple system. A single tight binary pair might have its own entangled magnetic field. Another pair orbiting the first could also be magnetically linked, and because the entire system is gravitationally bound, the stellar winds and plasma filling the space between these pairs can act as a medium to carry magnetic influence, allowing the separate magnetic networks to couple with one another. The result is a hierarchical magnetic web, mirroring the gravitational hierarchy, where local binary entanglements are themselves linked into a wider, system-spanning matrix. This web is in constant, turbulent motion, stretching, twisting, and storing colossal amounts of energy as the stars move through their complex orbits, perpetually reconfiguring the connections between them. This system-wide magnetic connectivity has a direct and dramatic consequence. It can synchronize stellar activity across vast distances in a way that seems to defy the isolation of individual stars. We see a hint of this in our own solar system, where the sun's activity follows an 11-year cycle of sunspots and flares. In a decuple system with entangled magnetospheres, this concept is elevated to an entirely new level. Observations have revealed stars whose flare activity and brightness variations appear to be precisely synchronized, even when they are separated by distances equivalent to the span of our entire solar system. It's as if these stars share a single, system-wide heartbeat. The mechanism is a form of cosmic feedback. When one star in the web experiences a buildup of magnetic stress and unleashes a flare, the resulting shockwave of radiation and high-energy particles doesn't just expand into empty space. It travels along the pre-existing magnetic highways of the web, channeled and focused directly toward its stellar siblings. This incoming blast of energy can jolt the magnetic fields of the other stars, pushing them toward their own instability thresholds. A flare on one star can therefore act as a trigger, setting off a chain reaction of eruptions across the system. This isn't a gentle domino effect. It's a coordinated barrage, a symphony of magnetic explosions where multiple stars unleash their fury in a tightly timed sequence. The energy released in such a coordinated event is not merely the sum of individual flares. The synergistic interaction between them can create a system-wide disturbance far more powerful than any isolated outburst. For any potential planets, this means there is no safe harbor. A world could be orbiting a seemingly quiet, stable star on the outskirts of the system, only to be bathed in a lethal wave of radiation that was triggered by a flare from a star halfway across the gravitational community. Its deadly energy delivered via the invisible magnetic tunnels that bind the stellar family together. The most extreme manifestation of this entangled state is the phenomenon of a hyperflare, a conjectured but terrifying possibility where the magnetic web channels energy from multiple stars into a single cataclysmic detonation. Picture the entire magnetic infrastructure of the system becoming overloaded. As the stars move into a rare, precise orbital alignment, the twisting of the magnetic fields reaches a critical breaking point. Instead of a series of sequential flares, the entire web could snap and reconnect all at once in a singular, coordinated collapse. In this scenario, the stored magnetic energy of several stars, not just the thermal energy of their nuclear furnaces, is liberated in a single, unimaginable flash. The resulting hyperflare would be a transient event of almost biblical power, a pulse of gamma rays and X-rays so intense it could, for a few seconds, outshine the combined light of every star in the system. The effect on the surrounding space would be apocalyptic. Planetary atmospheres would be scoured away in an instant, and any incipient life would be erased down to the microbial level, not just on one world, but potentially on every planet within the entire system. The discovery of this magnetic entanglement fundamentally changes our view of these systems. It reveals that the stars within them are not independent actors, but nodes in a vast, intelligent-seeming network of energy, capable of acting in concert in ways we are only beginning to comprehend. This invisible magnetic architecture proves that the true complexity of a decuple system lies not only in the gravity that binds the stars, but in the energetic conversations happening between them, conversations written in the language of magnetic force and spoken with the voice of stellar fire. After confronting the dizzying chaos of magnetic entanglement and relativistic projectiles, it might seem that every decuple system is destined for a life of relentless violence. Yet the cosmos has a way of delivering the most profound surprises, and none is more baffling than the discovery of what astronomers have come to call the quiet decuple system. Catalogued as a serene oasis amidst the stellar storm, this system, let's designate it Kappa Coronii for our discussion, presents a portrait of celestial harmony so profound it defies all expectations. Imagine a family of 10 suns, all gracefully tracing their orbits with the gentle precision of a well-rehearsed orchestra, with no violent flares, no titanic stellar winds, and no catastrophic close encounters. The data is unmistakable. Where other similar systems blaze with X-rays and flicker erratically, Kappa Coronei's emissions are a placid, steady hum. This profound tranquility forces us to reconsider the very nature of complexity, suggesting that having many stars doesn't automatically sentence a system to a short, violent life, but can instead lead to a state of deep, enduring peace. The question, of course, is how such a thing is possible. How can 10 massive gravitational engines coexist without constantly jostling one another into eruptions and collisions? The answer appears to lie in a fortunate combination of stellar demographics and exquisite orbital choreography. The first clue to this mystery is the advanced age of all its stellar members. In Kappa Coronii, every single star has settled into a comfortable and stable phase of life. They are predominantly older G-type and K-type stars, similar to our Sun but often a bit cooler, and they have left behind the fiery tantrums of their youth. A star's magnetic activity, which drives flares and powerful stellar winds, is fueled by its internal dynamo, a process driven by the convection of plasma and the star's rotation. As stars age, they gradually slow down, their rotation winding down like a spinning top finally coming to rest. This slower rotation calms the internal dynamo, leading to a dramatic drop in magnetic activity. In this system, it seems no star was ever a brilliant, short-lived O-type giant, the kind that churns the cosmic pot with its ferocious energy output. Instead, Kappa Coronii is a family of retirees, its members having long ago burned through their most volatile fuel and settled into a long, quiet middle age, emitting gentle, steady light with only the faintest whisper of a solar wind. Their collective radiance is like the warm, even glow from a bank of mature light bulbs, rather than the blinding, sputtering glare of a welder's torch. But an old, calm star can still be perturbed by a disruptive neighbor. This is where the second, more remarkable piece of the puzzle comes into play: orbital phasing. The stability of Kappa Coronii isn't just a happy accident of stellar geriatrics, it's a masterpiece of gravitational engineering. Through billions of years of subtle adjustments, the orbits of these 10 stars have evolved into a configuration where their most powerful gravitational influences are perfectly timed to cancel each other out. Think of it as pushing a child on a swing. If you push at random, chaotic intervals, the swing's motion will be jerky and unpredictable. But if you push at the exact right moment in each cycle, you create a smooth, stable, and predictable arc. In this system, the stars act as gravitational pushes for one another, but their orbits are phased in such a way that these pushes are almost perfectly compensatory. When one star tugs another inward, the combined pull from two other stars at that precise moment in their orbits tugs it outward, resulting in a net force of nearly zero. This delicate balance prevents any single star from ever being jerked into a disruptive, eccentric path that would bring it too close to a sibling. The entire hierarchy resonates with a profound stillness, the gravitational equivalent of a perfectly balanced mobile that hangs motionless in still air. This phasing extends to the system's tidal forces as well. In chaotic systems, close passes generate immense tidal stretching, pulling stellar atmospheres apart and triggering mass transfer. In Kappa Coronii, the orbits are likely arranged in concentric, well-separated shells. The inner binaries are tight, but their orbits are circularized, ensuring a constant, gentle pull rather than a violent, periodic yank. The wider orbits of the outer stars are so vast that their gravitational influence is diluted to a soft, background whisper. This arrangement means that the stars never pass close enough to one another to raise significant tidal bulges on their surfaces. There are no streams of stolen plasma, no stellar spaghettification, and no violent rejuvenation of old stars. Each sun is left to burn its fuel in peaceful isolation, its evolution proceeding along a natural, predictable course, untouched by the dramatic interventions that reshape the lives of stars in more violent systems. The quiet of Kappa Coronii is not the silence of emptiness, but the deep, resonant quiet of perfect equilibrium, a state that may allow it to endure, unchanged for many billions of years to come, a timeless and serene monument to the possibility of harmony in a universe so often defined by chaos. But what happens when this gravitational dance becomes a little too intimate? The crowded core of a Decuple system is a place of immense risk, a stellar freeway where the rules of the road are written by gravity, and sometimes catastrophic collisions occur. This brings us to a system with a violent secret hidden in its past, a cosmic cold case where the evidence points to a stellar homicide followed by a bizarre act of reincarnation. Astronomers studying a particular Decuple family noticed something deeply unusual about its brightest member. This star was an outlier in every way. Its mass was far greater than any other star in the system, and its composition was a chaotic mess, with helium and heavy elements like carbon and oxygen burning furiously at its surface, a signature that should be buried deep in a star's core, not visible on the outside. This star was a cosmic Frankenstein, a monstrous hybrid that could not have formed through any normal process. It was a living relic of a past merger, the product of a head-on collision where two stars literally slammed into each other and fused into a single, bloated, and unstable entity. This kind of event is incredibly rare in the wider galaxy, but in the densely packed hub of a Decuple system, where stars whip around each other at high speeds in a confined space, the probability of such a catastrophe increases dramatically. To understand the sheer violence of this event, you have to picture the process not as a gentle melding, but as a cataclysmic demolition. Before the merger, two main sequence stars, each similar in mass to our Sun, were likely locked in a decaying orbit, their path slowly tightening over millions of years due to gravitational wave emission or perturbations from their many siblings. As they spiraled inexorably closer, the tidal forces between them grew exponentially, tearing at their outer layers and creating a shared, chaotic envelope of superheated gas. When they finally crossed a critical threshold, their cores plunged together in a final, devastating embrace. The kinetic energy of the collision was converted almost instantly into heat, causing a runaway thermal pulse that bloated the new combined star into a temporary, enormous giant. The fusion processes inside went haywire. Hydrogen that was once burning steadily in two separate cores was now violently mixed with the helium ash, creating a bizarre and short-lived object known as a blue straggler, a star that appears unnaturally young and hot for its environment because it has been forcibly rejuvenated by a massive infusion of fresh fuel and a new, more massive structure. The aftermath of this stellar fusion permanently rewired the system's gravitational circuitry. Before the merger, the system's stability depended on the precise dance of 10 individual masses. The sudden consolidation of two of those masses into one single, much heavier object was like replacing two small, fast-moving dancers in a ballet with one giant, slow-moving one. This altered the center of mass for the entire local group and sent gravitational shockwaves through the hierarchy. The new, more massive star exerted a stronger pull on its immediate neighbors, potentially tightening their orbits or flinging one of them out onto a more eccentric path. The merger also likely ejected a significant amount of material, the stellar equivalent of shrapnel, in the form of a hot, expanding shell of gas that would have temporarily filled the inner system, interacting with the stellar winds of the other stars and potentially triggering a brief, furious period of new star formation in the surrounding nebula. The system we see today is the calm after this ancient storm, its current architecture forever shaped by that one violent event. The presence of this merger product is a permanent monument to the system's turbulent past, proving that these complex families are not static paintings but dynamic, evolving ecosystems where stars can be born, can die, and can even be violently reborn in a single, spectacular instant. Within this celestial chaos of 10 suns, the universe sometimes lines up a perfect, fleeting alignment that transforms one star into a natural magnifying glass, offering us a direct and exquisitely precise way to weigh it. This phenomenon is known as gravitational microlensing, and witnessing it occur entirely within a single star system is one of the rarest and most valuable observations an astronomer can make. The principle is a dramatic illustration of Einstein's general relativity, where mass warps the very fabric of space-time. We often think of this as the bending of light around massive objects like entire galaxies, but the same physics operates on a much smaller, more intimate scale within a Decuple family. Here's how it works. When one star in the system, the lens, passes almost directly in front of a more distant source star from our viewpoint on Earth, its gravity acts as a temporary cosmic lens. It bends and focuses the light rays from the background star, causing that distant sun to temporarily brighten in a very specific way. It's as if nature itself is handing us a perfectly calibrated scale and a magnifying glass at the same time, allowing us to measure a star's mass with an accuracy that is nearly impossible to achieve by any other method. The signature of such an event is a perfectly symmetrical, predictable brightening and dimming of the background star's light. The light curve doesn't flicker erratically, it forms a smooth, bell-shaped peak. The star brightens steadily to a maximum as the lensing star moves into perfect alignment, and then fades away just as smoothly as the stars continue on their separate paths. The duration of this event is critically important, and in a Decuple system, it can be incredibly brief, lasting only a few days or even hours. This is because the stars are relatively close together and moving at high orbital velocities, so the period of perfect alignment is fleeting. Capturing such a transient event requires immense luck and relentless automated monitoring of the system. Astronomers use powerful survey telescopes that scan the same patch of sky night after night, meticulously measuring the brightness of thousands of stars within the Decuple system, hoping to catch one of them in the act of this celestial magnification. It is a cosmic paparazzi waiting for the perfect shot, a moment when the gravitational choreography of the system creates a perfect straight line from a background star through a foreground star and all the way to our telescopes. The true power of this micro-lensing event lies in the data encoded within that smooth light curve. The duration and shape of the brightening peak are directly tied to the mass of the foreground lensing star. A more massive star will create a stronger gravitational lens, bending the light more sharply and producing a wider, more prolonged brightening. A less massive star will create a narrower, quicker peak. By fitting a mathematical model to the observed light curve, astronomers can derive the mass of the lensing star with an uncertainty of just a few percent. This is a monumental achievement. Typically, measuring the mass of a solitary star is notoriously difficult. It requires it to be in a binary system where we can observe its orbital motion. But micro-lensing allows us to weigh a star even if it is completely isolated, or if it is one of the many faint, dim members of the system that are usually lost in the glare of their brighter siblings. This technique has been used to confirm the nature of suspected brown dwarfs within these systems, providing a definitive mass measurement that separates these failed stars from true, fusion-powered red dwarfs. It acts as a cosmic weigh station, giving us a direct, unambiguous reading of a star's gravitational influence, which is the most fundamental property determining its life and ultimate fate. Beyond simply weighing stars, these internal micro-lensing events offer a second, equally precious gift: the ability to probe the atmosphere of the background source star in unprecedented detail. As the lensing star moves across the face of the background star, it doesn't just magnify the star as a single point of light. It acts like a giant lens scanning across the disk of the background star. This allows for a technique called lensing parallax, where subtle asymmetries in the light curve can reveal tiny features on the background star's surface, such as star spots or differences in brightness across its face. For a brief moment, our view of that distant sun is sharpened to a resolution that would normally require a telescope thousands of kilometers wide. We can effectively map its surface, studying its stellar activity and composition in a way that would be utterly impossible without the fortuitous intervention of a gravitational lens. This turns a rare alignment into a powerful analytical tool, letting us study one star in exquisite detail by using the gravity of another as our instrument. In the grand, tangled web of a Decuple system, these fleeting moments of cosmic alignment are like sudden flashes of clarity, where the complex dynamics of the family create a perfect laboratory for testing our most fundamental theories of physics and peering into the hearts of distant suns. Just as the inner planets in a decuple system face a constant barrage of radiation and gravitational chaos, the outermost reaches of such a system would be home to a celestial shooting gallery of unimaginable scale. In our own solar system, we have the Oort cloud, a vast spherical shell of icy planetesimals and dormant comets that encircles us at a distance of nearly 1 light-year, a relic from the solar system's formation that remains largely undisturbed. Now envision a similar cloud of trillions of icy bodies surrounding a family of 10 suns. The gravitational reality for this distant shell would be a relentless, multi-directional tug of war. Unlike our sun's solitary and gentle gravitational sway, the combined pull from 10 different stellar masses, each orbiting a shared center and constantly changing position, would turn this serene reservoir into a violently churning sea. The orbits of these pristine, ancient ice balls would be anything but stable. The subtle, rhythmic gravitational nudges that keep our own Oort cloud in a state of quiet equilibrium would be replaced by sharp, unpredictable yanks from multiple directions. A comet peacefully orbiting in the outer darkness would suddenly feel the focused pull of a binary pair swinging through the apogee of its orbit, or the more distant but still potent influence of a solitary star on the far side of the system. This constant gravitational perturbation acts like a cosmic pinball machine with the 10 stars as the flippers, perpetually launching these icy bodies onto new and often dangerous trajectories. The most direct consequence of this stellar agitation is a dramatic and unending cometary bombardment directed at the system's inner regions. In our solar system, a comet is jostled inward from the Oort cloud only on rare occasions, perhaps by the gravitational nudge of a passing star or the tidal force of the Milky Way itself, leading to a long-period comet visit every few thousand or even million years. In a decuple system, this process is not a rare event, it is a permanent state of affairs. The rate at which comets are dislodged from their distant orbits and sent plunging toward the inner stellar family would be thousands of times higher than in our own quiet neighborhood. The sky of any inner planet would be frequently streaked with the brilliant glow of new comets, their tails of vaporized ice painting temporary arches across a heavens already filled with multiple suns. This would not be an occasional celestial spectacle, it would be a constant looming environmental threat. A significant fraction of these inbound comets would not simply make a graceful loop around the central stars and head back out. Their chaotic paths, further complicated by close gravitational encounters with other stars in the system, would ensure that many cross the orbits of the inner planets. The result is a perpetual and heavy bombardment, a cosmic hailstorm where large, icy impactors could strike a world with a frequency that makes the early solar system's late heavy bombardment seem like a light drizzle. For any world clinging to life in such an environment, this relentless barrage presents an existential challenge that would fundamentally shape its evolution. An atmosphere, that delicate shield that protects a biosphere from radiation and regulates temperature, would be under constant assault. A single large cometary impact can inject enough energy and vaporized rock into an atmosphere to trigger a global firestorm or a years-long impact winter, as the dust high in the atmosphere blocks out the light of the stars. On a world in a decuple system, these extinction-level events would not be once-in-an-eon catastrophes. They could occur on timescales of hundreds of thousands or even tens of thousands of years. This creates a brutal evolutionary filter. Life would need to be incredibly resilient, capable of recovering from global sterilizations with astonishing speed, or it would need to find a refuge safe from the surface cataclysms. The most likely cradle for life might shift entirely underground, to vast, insulated subsurface oceans where the thermal stability of the planetary interior could provide a buffer against the chaos raining down from above. The very chemistry of the planet would also be continually altered. Comets are rich in water ice, organic molecules, and volatile compounds. This constant delivery of raw ingredients could, in one light, be seen as repeatedly reseeding the planet with the building blocks of life, potentially restarting the clock of biogenesis over and over. However, it is a double-edged sword. The same impacts that deliver water and organics also possess the sheer kinetic energy to boil away oceans and shatter those complex molecules, creating a frustrating cycle of creation and destruction that could prevent life from ever advancing beyond the most primitive, hardy forms. This chaotic Oort cloud also reshapes our understanding of planetary system architecture itself. In our solar system, the Kuiper belt and the Oort cloud are relatively pristine and well-ordered, a testament to a calm evolutionary history. In a Decuple system, the equivalent of the Kuiper belt, a closer-in disk of icy debris, would likely have been utterly demolished long ago, either ground to dust by collisions or completely ejected by gravitational encounters. The fact that an Oort cloud can even persist in such an environment is a surprise. It suggests that while the inner regions are constantly being scoured, the sheer volume of space at such immense distances allows a reservoir to survive, albeit in a state of perpetual turmoil. The comets we would see are not the pristine, ancient relics from the dawn of the system. They are a constantly refreshed population, with older members being ejected into interstellar space or destroyed, and new ones being constantly perturbed inward from slightly more stable orbits further out. The entire cloud behaves less like a static archive and more like a dynamic, living entity, its population in a steady state of flux, governed by the chaotic rhythm of its 10 gravitational masters. This transforms the Decuple system's Oort cloud from a quiet museum of solar system history into the primary engine of environmental change. An ever-present force that ensures the inner planetary system remains a frontier of both danger and opportunity, where the seeds of worlds and the seeds of life are perpetually sown and just as perpetually threatened. Of all the orbital oddities we have encountered, one of the most perplexing discoveries is that of a system where an entire family of stars seems to be breaking the rules of the cosmic dance, moving in a direction completely contrary to the flow. In this specific Decuple system, astronomers mapped the complex orbital paths of all 10 members and found something that defied standard models. One distinct subgroup, a tight quadruple system, traces a wide, looping path around the common center of mass in the exact opposite direction to the other 6 stars. This is a retrograde orbit on a grand scale, a celestial rebellion where a significant portion of the stellar family is moving against the grain, like a group of dancers suddenly and inexplicably deciding to waltz counterclockwise while everyone else spins clockwise. This isn't just a minor anomaly, it's a fundamental challenge to our understanding of how such intricate families are born. The prevailing theory of star formation dictates that a single, collapsing cloud of gas and dust will possess a net angular momentum, a preferred direction of spin, much like a figure skater pulling in their arms to spin faster. Every star and planetary body that condenses from that single cloud should, in theory, inherit that same basic direction of rotation, creating a system where most orbits are prograde or aligned with this primordial spin. The presence of a massive retrograde group within a bound system is a glaring violation of this principle, a clear sign that this system's history is far more dramatic and interactive than a simple, isolated birth. The most compelling explanation for this celestial contrarian is a violent and ancient act of cosmic theft. This retrograde group of stars likely did not form alongside its current family members. Instead, it is almost certainly an adopted cluster, a group of stellar siblings that were born in a completely different stellar nursery with their own unique spin direction. Billions of years ago, the original system, perhaps a stable sextet of stars, had a fatefully close encounter with this wandering quadruple system. As the two groups passed by each other, their complex gravitational fields intertwined in a delicate slingshot maneuver. The immense pull of the larger system managed to rob the smaller group of just enough of its orbital energy, effectively capturing it. Instead of continuing on their original path through the galaxy, the four stars found themselves trapped in a new, wide, and crucially retrograde orbit around their captors. This process is the gravitational equivalent of a larger, faster ship pulling a smaller lifeboat alongside it and securing it with a rope. But in this case, the rope is gravity itself, and the direction the lifeboat is tied on is backwards. The retrograde orbit is the clearest possible evidence of this external origin, a permanent tag on these stars that reads "not from here." Their motion is a fossilized record of that long-ago encounter, a dynamic signature that they were not part of the original, co-rotating cloud. The survival of such an unstable-seeming configuration over billions of years is a testament to the delicate balances possible within hierarchical stability. The retrograde group isn't plunging through the heart of the system on a collision course. It is likely nestled in a very wide, stable outer orbit within the hierarchy. Its gravitational influence is smoothed out over such a vast distance that it doesn't constantly destabilize the inner prograde stars. Think of it as a large moon orbiting a planet in the opposite direction. While unusual, it can be stable if the moon is sufficiently far away. The system has found an equilibrium, albeit a precarious one, where the contradictory motions are managed through careful orbital spacing. This retrograde arrangement has profound consequences for the system's overall dynamics. It acts as a persistent source of gentle gravitational perturbation, subtly tugging on the other stars in a way that a prograde group would not. Over immense timescales, this can slowly torque and realign the orbital planes of the inner binaries, potentially driving a long-term, system-wide evolution that would be absent in a uniformly rotating family. The retrograde group is not just a passive prisoner, it is an active, if subtle, participant in constantly reshaping the gravitational architecture of its adopted home, ensuring that the system's story is one of ongoing change and adaptation, a permanent reminder of its violent and acquisitive past. But one of the most elegant and revealing discoveries in this field comes not from a violent explosion or a hidden object, but from a simple, continuous measurement of light. In a specific Decuple system, astronomers monitoring the combined brightness of all 10 stars over many years witnessed something that initially seemed like pure chaos. The light curve, the graph of its brightness over time, was a wild, scribbled mess of dips and peaks, a frantic, seemingly random scribble with no discernible pattern. But when scientists applied sophisticated mathematical analysis, filtering out the noise and stretching the timeline, an astonishing truth emerged. That chaotic scribble resolved into a perfectly rhythmic, repeating pattern, a precise and complex stellar heartbeat captured on a graph. This heartbeat light curve is the system's unique signature, a celestial EKG that records every gravitational interaction and celestial alignment as a distinct feature in its pulse. Each tiny dip is not just an eclipse, it is a specific star passing in front of another specific star. Each subtle peak is not a random flare. It is a predictable tidal brightening event where one star's gravity slightly squashes its companion, causing its facing side to glow more brightly. There are deep primary dips when a large, brilliant star is completely occulted by another massive body, and there are shallow, secondary dips when a smaller, fainter red dwarf transits one of the giants. The rhythm is dictated by the orbital periods of the various stellar pairs and groups, all superimposed on top of one another to create a symphony of light that repeats with clockwork precision over its full multi-year cycle. Decoding this cosmic cardiogram is a monumental feat of astronomical detective work. It is the ultimate orbital puzzle where the solution is the complete architecture of the entire 10-star family. Astronomers use the timing of each dip and peak like a set of clues. The duration of a dip tells them about the relative sizes of the stars involved. The depth of the dip reveals the contrast in their brightness. The precise interval between successive dips of the same type gives the exact orbital period of that particular binary pair. But the true power of the heartbeat lies in the more subtle effects. The slight, predictable changes in the timing of these eclipses arriving a few seconds early or late are the fingerprints of general relativity, the precession of orbits caused by the warping of spacetime. The gentle, rounded shape of a dip, as opposed to a sharp, square one, can reveal the presence of a diffuse atmosphere or a stellar wind being gently eclipsed. By meticulously cataloging every single feature in this intricate pattern and running countless computer simulations, astronomers can essentially reverse engineer the entire system. They can determine not only the orbits of all 10 stars, but also their precise masses, their diameters, their temperatures, and even their approximate shapes, all from the simple, patient act of measuring the collective flicker of their light from a distance of thousands of light years. This method provides a check on our understanding that is far more precise than any other. Spectroscopic measurements can give us the velocity of stars, but they struggle with complex systems where many stars' light is blended together. Direct imaging can show us positions, but it cannot easily reveal the all-important third dimension of depth or the precise timing of orbits. The heartbeat light curve synthesizes all of this information into a single, elegant, and testable model. It is the system's own confession, spelling out its structure in the language of light and shadow. The existence of such a perfectly periodic, complex heartbeat is also a profound indicator of the system's long-term health and stability. A chaotic, unpredictable light curve would signal gravitational turmoil, with orbits constantly changing and stars being perturbed. This rhythmic, repeating pattern is the signature of a system that has achieved a deep and resonant equilibrium, its members having settled into a gravitational harmony that allows their intricate dance to continue unchanging for countless cycles. It is the pulse of a cosmic giant, a perfectly tuned engine of gravity and light, whose every beat tells the story of its 10-sunned soul. And after exploring the chaotic birth of these systems and the violent mergers that can create stellar Frankensteins, we now arrive at one of the most profound and far-reaching discoveries of all: the potential for these 10-star families to act as cosmic crucibles for the most energetic and element-forging events in the entire universe. We're venturing beyond the death of single stars and into the realm of a kilonova, an explosion so powerful and so precious that it is responsible for creating most of the gold, platinum, and other heavy elements in the cosmos. The theoretical pathway to this ultimate cosmic alchemy begins with the grim remnants of the system's most massive stars. Throughout its lifetime, a Decuple system is a factory for stellar death. Its brilliant O-type and B-type giants live fast and die young, ending their lives in spectacular supernova explosions. What they leave behind are their ultra-dense, city-sized cores, neutron stars. These are objects so compact that a single teaspoon of their material would weigh billions of tons on Earth. In a less crowded environment, two neutron stars might simply orbit each other peacefully for billions of years. But within the gravitational whirlwind of a Decuple system, peace is not an option. The constant, subtle gravitational prods from the other 8 stellar members act like persistent nudges on this binary pair of stellar corpses. Every time a passing star tugs on the system, it transfers a tiny amount of energy, slowly but inexorably altering the neutron star's orbit. Over millions of years, these cumulative perturbations cause their paths to decay. They spiral closer and closer together, losing orbital energy that is carried away in the form of faint, rippling gravitational waves. This process of gravitational driving is vastly more efficient in a Decuple system than in an isolated binary. It's the difference between a single person trying to push a heavy box and 10 people all giving it coordinated, sequential shoves in the same direction. The system's complex gravity acts as a relentless engine, continually tightening the screws on the neutron star binary and accelerating its journey toward a cataclysmic finale. The final act of this billions-year-long drama is the merger itself. When the two neutron stars finally cross a critical threshold, they plunge toward each other in a final, frantic dance. In the last milliseconds, they tear each other apart with immense tidal forces before colliding in an event that unleashes more energy than all the stars in the galaxy combined. This is the kilonova. The collision does two extraordinary things. First, it blasts a hot, neutron-rich fireball out into space. Within this expanding cloud, atomic nuclei are bombarded by a tsunami of free neutrons in a process known as rapid neutron capture, or the R process. In a matter of seconds, nuclei grow at an astonishing rate, climbing the periodic table to form the heaviest stable elements like gold, platinum, and uranium. A single kilonova can forge hundreds of Earth masses worth of gold and other precious metals, scattering this cosmic treasure across the interstellar medium. Second, the violent merger shakes the very fabric of space-time, sending out a powerful, unmistakable chirp of gravitational waves, a signal that our detectors like LIGO and Virgo are now tuned to hear. The Decuple system, therefore, becomes an incredibly efficient factory for these events. Its unique environment not only creates the necessary neutron star binaries through its history of massive stars and supernova, but also provides the persistent gravitational agitation to drive them to merge on timescales that are short compared to the age of the universe. Without such dense stellar environments, these mergers might be too rare to seed the galaxy with the heavy elements necessary to form rocky planets like Earth, and ultimately life itself. The gold in your jewelry and the uranium that fuels nuclear reactors were likely forged in the heart of a kilonova, and there's a strong possibility that the trigger for that cosmic forge was the complex, relentless gravity of a system not so different from the ones we've been exploring. Looking across a timescale that dwarfs the entire history of our planet, the ultimate destiny of a Decuple star system unfolds not as a single event, but as a slow-motion gravitational unraveling, a cosmic drama written over tens of billions of years. Supercomputer simulations, which model the complex interplay of every gravitational nudge and tidal pull, reveal a future that is both violent and strangely serene. The initial phase is one of gradual erosion, where the delicate hierarchical architecture that granted the system its longevity begins to fray at the edges. The outermost stars, those tracing the wide, slow orbits around the central core, are the most vulnerable. Over eons, the cumulative gravitational influence of passing stars from outside the system, and even the tidal pull of the Milky Way itself act like a persistent, gentle breeze on a house of cards. One by one, these distant members are stripped away, their gravitational bonds to the family severed. They drift off into the galactic darkness as solitary runaways, their light fading as they join the vast population of interstellar orphans, leaving the system slightly smaller, slightly less complex with each departure. This slow dissolution gives way to a more dramatic and active phase of internal consolidation. As the system sheds its outer members, the remaining stars are drawn closer together by the relentless pull of dynamical friction. The once stable orbits protected by resonant harmonies begin to feel the strain. The gravitational perturbations that were once manageable now become amplified in the tighter confines. Close encounters, once rare, become commonplace. This is when the stellar collisions begin. Two stars, swung onto intersecting paths by the chaotic gravity, fail to miss each other. Their collision is not a fiery explosion in the traditional sense, but a violent merging, a tumultuous fusion of two spheres of plasma into one, larger and often unstable star. This new Frankenstein star burns with a strange intensity, its life cycle abruptly reset and accelerated. It may live for only a short, brilliant period before itself collapsing into a stellar remnant. These merger events release flashes of intense energy and gravitational waves, each one a tremor that further destabilizes the orbits of the remaining stars. The system is now eating itself, consolidating its mass into fewer, more massive objects. The final act of this cosmic consolidation is a rapid-fire sequence of gravitational slingshots and ejections. The system's core becomes a frenetic arena where 3 or 4 massive remnants, neutron stars and stellar mass black holes, now dominate the gravitational landscape. Their interactions are extreme. In a complex gravitational dance, a close pass between 3 of these objects will almost inevitably result in one of them being flung out of the system at an incredible velocity. This process, known as the gravitational slingshot, acts as nature's mechanism for removing excess energy and angular momentum. The ejected object, whether a neutron star or a black hole, is hurled into the galactic halo, a dark projectile that will likely never interact with another star again. With each ejection, the system becomes simpler, quieter, and more stable. The simulations consistently converge on a single, elegant endpoint. After all the chaos, the slow evaporation, the violent mergers, the dramatic ejections, what remains is not a complex Decuple system, but a much smaller, incredibly durable configuration. The most probable final state is a tight binary, 2 stellar remnants like black holes or neutron stars, locked in a final, intimate dance. They orbit each other in a whirling embrace so close that their orbital period might be measured in mere hours. In some scenarios, a third remnant remains, tracing a much wider orbit around this central binary, creating a stable triple system of the dead. This end-state binary is the ghost of the system that once was. These black holes or neutron stars are the dense, fossilized cores of the most massive stars from the original family, the last survivors of a once vibrant community of 10 suns. Their dance is a silent one, emitting no light, only a persistent, faint hum of gravitational waves as they slowly spiral inward. They will continue this final waltz for trillions upon trillions of years, long after every other star in the galaxy has burned out, their eventual merger marking the very last flicker of activity from a system that was once a pinnacle of cosmic complexity. The journey from a bustling stellar metropolis to a quiet, dark binary is the ultimate fate of these gravitational marvels, a testament to the fact that even the most magnificent and chaotic structures in the universe are ultimately transient, destined to be simplified by the relentless and patient hand of gravity. From the delicate gravitational clockwork of resonant orbits to the apocalyptic fury of system-wide superflares, from stellar zombies endlessly reborn in nova fire to dark, hidden black holes silently stalking their families, the 30 discoveries we've explored reveal a cosmos of staggering diversity and sheer, unbridled strangeness. We have witnessed planets enduring chaotic orbits through the fleeting intersections of multiple habitable zones, stellar runaways catapulted into the void by gravitational slingshots, and entire systems enriched with cosmic gold forged in the violent mergers of neutron stars. We have seen magnetic webs synchronizing stellar heartbeats across billions of kilometers, ancient stars captured from other families creating retrograde rebellions, and the serene, almost impossible tranquility of systems where 10 suns have found a billion-year peace. Each of these findings peels back a layer of the universe, showing us that what we consider normal in our quiet solar system is but a single, simple melody in a galactic symphony of infinite complexity. Decuple star systems are far more than mere astronomical curiosities. They are the ultimate extreme laboratories, natural experiments that push the laws of physics to their absolute limits. They force us to test general relativity in the strong field regime, to watch the life cycles of stars be rewritten by gravitational interactions, and to reconsider the very fundamentals of where and how planets, and perhaps even life, can arise. They demonstrate that chaos and order are not opposites, but can coexist in a delicate, hierarchical dance that persists for eons. In these crowded stellar metropolises, we find the keys to understanding everything from the origin of the heaviest elements to the final fate of all star systems. They challenge our assumptions at every turn, proving that the universe's capacity for wonder is truly limitless. This journey to the frontier of astrophysics has been one of constant surprise, and now we want to hear from you. Of all these mind-bending revelations, which one reshaped your understanding of the cosmos the most? Was it the concept of a planet with 10 different suns in its sky, the terrifying reality of a stellar hyperflare, or the elegant proof of curved spacetime written in the timing of eclipses? Share your favorite discovery in the comments below. We read every single one. If you enjoyed this voyage into the mysteries of deep space, make sure to subscribe and hit the bell so you don't miss our next exploration into the wonders of the universe. The cosmos is vast, strange, and full of secrets waiting to be uncovered, and we are just getting started.